happen. So
Yeah.
maybe in the
The
future
one,
we'll get questions,
the
and I
one
look
topic.
forward to it.
Yes, Manoranjan, sorry.
Yeah. So shall we start?
We have already started, I think.
Oh, great. Sorry. Yeah.
Yeah,
Please go ahead then.
yeah.
Yeah, you're hearing me, right? It's good. Okay. Okay. So without further ado, let me spend 20 some minutes telling you about some work with matrix product states and motivated by the modeling of ultra cold atomic gases. So before I before I get to the topic, let me just mention the people that collaborated with me on this. So Sang Woo was a graduate student, the first one to work on this. Wei Sun was a postdoc around that time. Samantha Bautman was an undergraduate student that did some of the work. Then Son Tao was another graduate student. And now Clayton and Alexander are one undergraduate student and graduate student that are currently working with me. Clayton just finished undergraduate here and is about to, is just starting this week graduate school in NYU. And Alexander is working with me at UC. So this, the work of the first people, Sang-Woo and Kuei, was funded by DARPA 2-3 years ago, and then and now the work is funded by NSF. You might not know all these acronyms. So this is the Defense Advanced Research Projects Agency and Army Research Office and Air Force Office of Sponsor Research, or at least the Optical Lattice Simulator Project was the name of the project I was part of. And NSF, everyone probably knows, is National Science Foundation, and MOT is AMO theory, so atomic molecular optical physics theory, and CMMT is condensed matter and materials theory. Okay, so after all the acknowledgements, let's start actually talking about the things. So let me first frame it as a computational problem. So we want to study strongly correlated systems. We're interested in particular in, it's a broad topic, right? In systems of matter, strongly correlated. So let's focus on one-dimensional systems. And there's a number of systems that we're used to study both continuum and discrete models, and some are more natural in one case, some are more natural in the other cases. And I'm interested in particular in the cases when the more natural model is a continuous model. So one has a field theory, typically non-relativistic in the condensed matter case, unless one is looking at graphene or some topological material or something like that. And when one wants to study it computationally, one typically ends up introducing some kind of lattice discretization. So what is the way things go? So one has a quantum field theory, and one is interested in the solution. So we start here from the left, and one would like to end up here on the bottom circle. But the way of systematically doing that is by first introducing some discretization. So one has a lattice quantum field theory. Then one uses some kind of way of solving it, maybe exact diagonalization, maybe quantum Monte Carlo, maybe something else. And one has a solution for the lattice, and then one has to extrapolate that to the continuum and hope one can get rid of all the artifacts that the discretization might have introduced. And this is what is done not only in condensed matter, people doing lattice QCD, this is what they do. And one of course would like to, one is just interested in the solution, and if there was a way of going directly from the quantum field theory to its solution, that would be great. And so are there more direct routes? So, well, the way one uses different solvers in different cases, so there's no generic answer. So it really depends on the problem you're looking at. So we're going to explore possibilities for this solution in the particular case of one-dimensional models. So let me, motivated by taking the models you would use in the case of the lattice theory. And the best technique is, but perhaps the most limited, is exact diagonalization. So it's good because it's an exact description, but it's limited to very small systems. So one starts with a wave function that is some expansion that one can parameterize as some in terms of some expansion coefficients, these numbers C sub alpha, where alpha labels the states of some quantum system. For instance, here in the bottom, we have a spin chain, and the different orientations of the spin, we can think of them as bits, so ones or zeros, and so that we have a number, and so that labels the different states in the system on a side basis, and each of them can contribute to some wave function, can be the basis state in which one expands the wave function, and C alpha the coefficients in one does that. And well, the dimension of the Hilbert space, the number of coefficients of these complex numbers C sub alpha that we need grows exponentially with the number of spins in the chain that we are considering. So that's the challenge for exact generalization approaches, and an exponential wall, and that one has to overcome. And how to do that? So there's an idea that I'll get to in the next slides, which is density metrics renormalization group, which one way of thinking of it is as a compressed way of doing exact generalization. And so overcoming this exponential growth. So what is the, let's take the more modern view of, we'll talk about both, but let me start with a more modern view of DMRG, which is based on something called matrix product states. That's what I call MPS there on the left written in green. So what is it? So the starting point is to look at these coefficients, and so they have an index that is alpha that comes with the different bits, but we can split this, here it will be a byte, exactly 8 bits, right? But we can split it into two half bytes, one with 4 bits and another with 4 bits. And arbitrarily, you can introduce some notation and call one side the system and the other side the environment. That's what we are going to do later when we talk in the DMRG language. And when one does that, so if we have, let's start with 4 bits, one can take one apart and keep the others. So instead of having a vector of coefficients C indexed by alpha, now because alpha, instead of a single number, we are thinking of it as 2 numbers. So it has 2 indices, this vector. So now we are dealing with a rectangular matrix that has, let's say, these 3 indices label the rows, and this labels the column, or vice versa, whichever way you like. And so one can do something that to that matrix, something that is called singular value decomposition, that corresponds to rewriting that matrix as the product of 3 matrices, one with the column indices, one this square here with the row index, and one matrix that connects the two is a diagonal matrix, is the matrix of the singular values. And well, that can always be done actually. And one can repeat that. And so then if I iterate that, then I get a more complicated structure of that type, and I keep doing it until I separate all the bits. And so I end up with a matrix, so a bunch of, these are unitary matrices actually, and these rhombus are diagonal matrices that contain the singular values. And the singular values have very nice properties. They're always real and non-negative, and one can use that property to one's advantage. So this is a little bit of a longer description that we need. So we can combine them, these dotted boxes, we can combine 2 matrices, do the product and get them together. So what we have is a product of matrices, we call this A's, with these physical indices, and this procedure of doing the singular value decomposition introduce these horizontal lines, which is some auxiliary space on which these matrices are multiplied. So this coefficient that we started with, this C sub alpha, is written at the end of the day as a product of some matrices. So we went from the top row here, where we have this C sub and alpha, writing explicitly this bunch of numbers, which are the states of the bits that I was introducing, but in general, could be more general, could be some local Hilbert space that takes D values. This is what this D is. And we have D to the N coefficients when we have N local Hilbert spaces in our chain. And we rewrite that as the coefficients as this product, like that. So now what we achieve is that now these matrices are associated to the different local states in the chain. And so we can use symmetries, for instance, translational symmetry. If the system is translational invariant, then there's no way really to difference what we call site number 1 in the chain on site number 2. Let's imagine we put the periodic boundary conditions to make it simpler, but it continues to be true actually with open boundary conditions or more general types of boundary conditions. And then there's really no information to this index 1, 2 to n on these matrices. It should be the same set of matrices for all the sites. So we can drop that index, and instead of having n times d distinct matrices, we have only d distinct matrices. So we achieved a big reduction in the size of our problem by appealing to symmetries, by implementing symmetries that of course, you can implement as well in these coefficients, saying that these coefficients with different values are related in some way. But in this parameterization, there's a very natural and simple way of doing it. And okay, so we can then do that kind of thing. So that we have these practical questions listed here on the left, which are about how to determine once we decide to adopt this parameterization, how to determine these matrices, what are the properties. I just discussed some of the properties that we expect, for instance, based on symmetries. And the other question is whether these matrices can be approximated. And that's also a place where we are going to gain something by doing things this way. So to motivate that, let me now, I already talked about the singular values, and I could be talking in that language, but let's make it a bit more physical. So let's discuss it again, but in a more physical language. So again, we have the wave function expanded in a basis, and let's say I split my chain in the 4 bits on the left and the 4 bits on the right, and I call one half the system, the other half the rest of the universe or the environment. So now the coefficients are coefficients that have one index in the system, one index in the environment. And let's imagine we have an operator that acts only on the system, some local operator in the part of the big system that we call our system. So if we take some expectation value of it, we see that the part corresponding to what we call the environment drops out, and we have these matrix elements of the operator that lives only on the system. Because it lives only in the system, you know, it has no really non-trivial matrix elements in the environment. That's how that drops out, making some delta function appears. And so we get this coefficient C combined in this way, C star C. And that, once we sum over the dummy index, that defines actually an object that we call the reduced density matrix. And so the expectation value is the trace of the operator times the reduced density matrix, a formula that you are, I didn't write it in that compact language, but you know, it's a formula that you are familiar with from quantum statistical mechanics. And so imagine you can diagonalize the density matrix. So then if you keep the largest eigenvalues of the density matrix, that would be a systematic approximation that would be good for arbitrary observables A in any part of the system. So, but diagonalizing the reduced density matrix actually is equivalent to finding to doing the singular value decomposition. And so repeated singular value decompositions then is similar to constructing based on the reduced density matrix a systematic state of matrix products. And the largest eigenvalue, then the larger singular values are the most important for calculating observables. So there's a systematic way in which we can truncate the system. And you're familiar with this. Actually, singular value decomposition is part of the JPEG algorithm to compact photographs, you know, pictures that you take with your cell phone. And you can see how on a grayscale image, the full image is that, and if you keep a 10% of the singular values, how it looks, it's a little bit more grainy, but still pretty good. And if you keep only a 1%, it starts to look not so discernible, but still there is something that emerges. So the point is that this can also be done for wave functions of many-body systems, and that's in modern language the insight that Steve White had when he introduced DMRG density metrics normalization group in his landmark 1992 paper. And so what is, so it was a few years later that people after White's work, that people understood the connection between DMRG and matrix product states that are equivalent. But so DMRG is a more physical way of thinking about it in terms of density matrices, and you know, more like a StatMech kind of language. And matrix product states is a more abstract way of thinking about it in terms of these singular value decompositions or other types of decompositions of that sort. But that language is the language in which, more mathematical language is the language in which we can ask, okay, what happens if this decomposition is actually done on some arbitrary discretization, and we want to systematically refine that discretization and take the limit of lattice spacing going to 0. And that question was answered about 10 years ago. And that gives rise to a formalism called the continuous version of matrix product states. And let me tell you what is that. So I'll be talking later about the Godin-Yang model. So let me start, let me just feature that model for example. And instead of having a trace of matrices acting on some basis of states, what we have is a second quantized formulation using the product, this piece, a path order exponential, similar to a time order exponential, but ordered instead of in time, in space. So along the one dimension that we have in space, we have a path order exponential with these matrices Q and R and the second quantized operators acting on the vacuum of the system. So this is equivalent to, you know, if you introduce a discretization, you can show that this is equivalent to a matrix product discretization that we just argued is something very generic that you can actually always do and has some nice properties that allow you to truncate and compactify the amount of information in the system. So we want to try to describe, this is already taking the limit of A going to 0. So taking the continuum limit. So now these matrices Q and R that enter in the exponent are the ones that that parameterize the system. You know, you can think of it as matrices of variational parameters. And again, we can use symmetries like translation invariance will give matrices that are not depending on the position, or actually you need something a little bit more general. So we show that in some cases we need this more general ansatz, a bit more like block wave functions kind of thing. And then there are some conditions that for a problem like Godin, and with this you're done for bosons, but if you have problems like fermions, you need additional requirements, like the matrices have to have the same properties as local operators. So have to have some anti-commuting properties, and for the same matrix is actually that actually connects to nilpotence. So there are ways of parameterizing these matrices. That was part of our work for the case of fermions. And let me not go in details, but this is based on Jordan forms parameterizations of these matrices. And well, you can see that it does well for bosons. That was what people in the original paper shown, that D is the size of the matrices Q and R, so it's called the bond dimension. As you increase the bond dimension, you quickly approach the exact result that in a model that has the same form as the one I'm talking, but for bosons instead of fermions. That's called the linear model, and is solvable with better answers, so you can see how you approach exact solution. We also played with trying to use this parameterization of matrix products instead of the usual one in the lattice, and look at the transfer field Ising model, which is also exactly solvable. And we show that for a very modest matrix size, you actually get pretty nice results. Of course, in the lattice, you can use the standard matrix product, but this was kind of a proof of concept. And then I can go and talk about fermions. So this is motivated by the experimental case of the Godin-Yang gas. In the case when you have different amounts of spin up and spin down fermions. Let me go very quickly because I think I'm going a little bit short in time. So
You have 5 minutes, Carlos.
Sorry?
You have 5 more minutes.
5 more minutes. Yes, that's why I'm kind of skipping a little bit here. So there is a motivation that in one dimension, this connects actually when you introduce an imbalance between up and down, this connects with how would you expect superconductivity to behave in the case of imbalance in more dimensions, and that connects to the work of Full de Ferrel and Larkin-Ovchinnikov. So it's called as FFLO states. So that's a physical motivation. You can see the references here, and has even astrophysical implications. So if you want to use superconducting ansatz, BCS type of ansatz for things like color superconductivity, which is relevant for astrophysical context, and strong coupled plasma and stuff like that, quark gluon plasma, then you need to consider this more general kind of ansatz than the BCS ansatz, the one by these four gentlemen. So this was then trying to test this kind of superconducting states is something that people wanted to do in the lab, and they found that in 3D was unstable, and so it could not be tested except in some metastable situations. But we know on theoretical grounds that it should be stable in 1D. So experiments were done in 1D, and this is, in the bottom you see the trap profiles, and which is what experimentalists will call atoms measure, and you see how at the end of the day measuring the radius of the different atomic clouds and mapping it radius and polarization that matches the lines which are actually from theory, and there is no fitting parameter. So this was a very nice agreement. There's no parameter to fit, so it's a non-trivial agreement between theory and experiment. It was a tour de force experimental achievement, I would say. And so it's a very nice model it's a very nice model and physical situation with rich physics to test the CMPS. So that's what we did. So we take the phase diagram and we go around this in order to visit all the different phases and check whether we capture the physics of each of them. We will move along this gray circle that visits all the different phases. So as you do that, we see the energy or free energy as a function of where you are in the phase diagram, and for different bond dimensions, this D, and you see how you approach systematically the Bethe ansatz solution, which is in black, and you can compute the density profiles. This is the plot on the top, which is what is measured experimentally, as I showed you. And you can go beyond, to things that are not easily available from the Bethe ansatz solution, which is the computation of correlators. What we did more recently was that we are in the process of writing, starting to write right now, is look more carefully at density-density correlators for different cases. And we look at the bosons, different types of fermions, and we actually are looking at Bose-Fermi mixtures as well. And you can capture already for very modest bond dimensions, you can capture very nicely the features of these correlators, because these are two particle correlators, and actually the MPS or CMPS expansion is an expansion really in a size of multi-particle entanglement clusters. And so with dimension equal to 4, we capture very accurately two particle entanglement. And that's what you need for two particle correlators to capture them very nicely. So you would need to, if you want three particle correlators, you would need to go one notch up in bond dimension. I've shown you that it's working for ground state properties, but it's also useful because it will, it's not, the formulation is not limited by special properties of the model like being integrable. So far I show you integrable cases and how you can match the solutions coming from Bethe ansatz. But let me show you very briefly what happens if you break integrability. So I changed the mass and put a different mass for up and down. And the phase diagram is modified. So in the inset is the phase diagram as it was for the mass balance case. So for mass imbalance, it gets skewed to the right. And you see the panel on the right is, now you don't have an exact solution, but you have a very similar type of systematic convergence as a function of a bond dimension, and starts at the volume of the gen solution and systematically improves over it as you increase bond dimension. So one can use this to predict trap profiles, and now the trap profiles can be richer. If you sit yourself on the right side of the phase diagram I flashed 2 transparencies ago, you can see that the trap profile you would obtain is a reentrant one, where the equivalent of the red lines in the experimental trap profiles that I showed you before. This is the polarization trap profile. Here is in green, and you see that it's non-zero, and then then it decreases. There's a plateau at 0 for the fully paired region, and then it becomes, with the opposite sign, but I'm plotting the absolute value, becomes non-zero. And this is done for very realistic values for 2 species, lithium and potassium, that have, of course, different masses, and you can mix in a trap experiment. And there are experiments that mix lithium and potassium in 3-dimensional clouds. So what you need to do is combine that expertise with the expertise of people that can confine the system in elongated traps to get it to be 1-dimensional, and you will be able to be measuring these kind of things. So it's a very realistic setting. And so let me summarize. So there's a large class of problems that is formulated more naturally in the continuum. MPS requires a lattice, but we can use CMPS. We validated it. I showed you it works for bosons, works for fermions. We are also working on mixtures of the two. In general, it's not limited by integrability, and that's it's a versatile tool. We might want to go what lies in the future ahead. So one might want to go beyond 1 dimension, and that's a nice challenge that has been a challenge forever in the matrix product states, but maybe in the context of CMPS, one can do things a little bit differently, and it's not so hard. And one advancement that happened in CMPS, in MPS about 15 years ago, was time dependent. So time dependent DMRG, time dependent MPS. One can try to think about time dependence in the context of field theories and continuum matrix product states. That's another very interesting direction for further studies. So I'm more or less hitting my time limit. So thank you for your attention, and I'll be happy to take any questions if there are any.
Yeah, thank you very much, Carlos, for a nice talk. And now we can have some questions. Questions, please. Okay. Okay, so I have a quick question. So how do you incorporate the CMPS for systems of dipolar quantum gases, or it is not feasible to incorporate CMPS for non-local interactions and so on?
You can. There is well, I mean, that's a frontier. There is, as far as I remember, only one paper looking at local interactions. Is kind of Yukawa kind of interactions. They decay pretty fast. So dipolar is a bit more longer range. So one would need to explore how one can make it work.
Right, right.
I could pass you the reference on the Chicago interaction, and that's the only paper that I'm aware of that looked at non-local interactions. But in principle, it's possible. So what? Yeah.
Okay, so we have one more question by Bikram Tripathi. Bikram, maybe you can ask your question.
Hi, Carlos. So I wanted to ask if it's possible to calculate wave function overlaps in particular. Like I can understand that this method is very powerful for calculating expectation values and avoid the exponential trap. But what about wave function overlaps? Let's say I calculate some eigenstate and I want to measure its overlap with some arbitrary state.
Wave function overlap between two different states.
Yes.
Uh,
Suppose I just want wave functions, not expectation values.
Right. So, well, I mean, you can compute the norm, and you can compute green functions, and that would be, you can, that's taking expectation values of some given operator on the ground state, for example, and now a wave function overlap will be the expectation value of the between the ground state and some other arbitrary state, or some state that you get after some time evolution or something. I think there is I think you could derive formulas, but I don't have a ready answer for you. But I think that, given that we can do other type of correlators, the one like this correlators, and in general we can compute green functions as well. There are even in the original paper there are some green functions for the linear case shown. So we can also do other things. So the thing is that this has been mainly applied for ground state properties so far. If you want to overlap between two different states, you probably want to maybe study something like kind of
That's right.
catastrophe, like do the ground state and then switching on some perturbation and do the ground state again and do get the overlap between the two or something like that. That that can be done. I believe it can be done, and one has to sit down and derive the formulas.
Okay.
Thank you.
So we have one more quick question from Mona Lisa. Is this method capable of calculating excited state properties? For example, dynamical responses.
Well, so I said you can compute green functions. So so that's part of that that kind of information is there. Computing excited states is see, basically you have to connect with what is done with the MRG. You can probably also do it here, but there's a lot that has been done with MRG that has not yet been done here. So for instance, time dependence, I said, is something that has been done with MRG in the last 15 years, has been very fruitful, very successful. Has not yet been done with the same level of accuracy in here. So all that kind of things are, the answer is most likely yes, but it has not yet been done.
Okay. Okay. Thank you very much, Carlos. So now over to Manoranjan for the photo session.
So I request everyone kindly switch on your camera for a minute so that we can have. And system admin, please take care of that. Sanjay? Yeah. Bapi, please take care.
Manoranjan, your video is off.
Oh, I'm sorry.
Done?
Okay, sir. Done.
Okay. It's done?
Yes, sir.
Okay, very good. Thank you.
Thank you, sir.
So Tapan, please go ahead now.
Go take you this.
Okay, so the next speaker in this session is Professor Bikram Tripathi from TIFR, and he is going to talk about spin-ons in the presence of magnetic order and MBL approach. Bikram, please share your screen. Yes. So if you can go to the full screen mode.
Is it okay?
Yes, it's fine.
Okay, so thank you very much. I'm quite impressed that the QMAT series does not stop come any crisis or tragedy. And I hope this means it will continue like this for a very long time, not in an online manner, but the series itself. So thanks for the invite. So I'm going to mostly tell about stuff that I've been doing with my graduate student, Aman Kumar. And what I'm going to say is, of course, built on past KITAIV related work I've been doing with a bunch of people over the last many years. And I benefited greatly from discussions with Shonak, Kedar's former student who is now in Oxford, Kedar himself, Senthil, Bhaskaran, Shubro, uh, Sampath, Nandini Trivedi, and Subir. And we are funded by DST, and also I'm very grateful for TI for providing computing resources. Okay, so if you want to get more details about what I'm going to say now, you could look up these two papers or write to me. Okay, so brief background about the context in which I'm going to present this talk. So it's about the area of quantum spin liquids, and as many of you will agree that this rough definition is sort of good. You have strongly interacting quantum spin systems that show no long-range magnetic order in the ground state. And the origin is geometric frustration together with quantum mechanics, and low dimensionality helps, which is part of this geometric reason. So one particular way in which you can understand this geometric frustration to arise is to look at these three spin half particles on the corners of an equilateral triangle, and they are interacting antiferromagnetically. And it's clear that all three bonds cannot be satisfied. Um, Whereas if you look at a classical system of spins in the same configuration, you can have these 120-degree orientations, and you will be able to find a ground state which is magnetically ordered in some way. So this is how uh, frustration and quantum mechanics combine to give rise to some new thing which is not present in the classical context. Okay, of course, now we have numerous examples of putative and more confidently confirmed quantum spin liquid systems. And the earliest examples where such uh, phases were believed to be very central to understanding the overall behavior were in the context of high temperature superconductivity. And so there's this famous paper of Anderson, Bhaskaran, and Zhao, which said that, well, you can have singlets between pairs of spin half particles on this square lattice in a way similar to the resonating valence bonds in benzene, which was for example, in benzene, which was known for a long time. And so you can have the single and double bond structures alternating, and the actual wave function is a superposition of these two. And you can have also these not only these two types of structures on the left called Kekule structures, but somewhat less intuitive the structures on the right, three structures on the right called Dewar structures. They don't appear much, and in fact even in high TC these are like less important, I believe, than the left two ones. You also have examples of quantum spin liquids in Kagome lattice antiferromagnets, such as this material Herbert smithite, uh, in a wide variety of triangular lattice organic systems. You see indications of spin liquid behavior. In particular, in this one, I don't know how to pronounce it. It's a complicated material, but essentially a triangle lattice antiferromagnet. And today's talk will be about the Kitaev model on the honeycomb lattice, which was, of course, predicted theoretically. And now there is considerable interest in material realizations of the Kitaev model. So why are people so excited about these quantum spin liquid systems, given that there is no magnetic order in a real quantum spin liquid? Well, lack of magnetic order doesn't mean dull. And just because you cannot get interesting electrical resistivity data or some interesting magnetic order doesn't mean there's nothing to it. Often these materials, you can find them associated with topological order, which means the ground state can be degenerate. You can have phenomena like long range entanglement. You can have exotic excitations such as spin-ons and anions, as opposed to the conventional expectation that you have just magnon-like excitations in a magnet. Okay, so what is this spin-ons in particular, which excite people? Well, I'm giving you data from this triangle, organic triangle lattice Heisenberg antiferromagnet. This material has a very large Q revised temperature. It orders antiferromagnetically. No, it doesn't order antiferromagnetic. It shows a Q revised law with a theta CW of minus 375 kelvins. And down to millikelvin temperatures, you see no hint of magnetic order in this material. And normally you would think that if you take a system of interacting spin-up particles, you can create elementary excitations from the ground state by just flipping, say, a single spin somewhere and taking linear superpositions of these states. And this is what creates magnons in the system. So these are spin 1 bosons. But here, if you had bosonic excitations as your simplest elementary excitations, you would expect a T cubed specific heat. But if you measure the specific heat of this material, you find that it has a linear T specific heat at very low temperatures. And this is not something you can explain from a bosonic perspective, but it's easier to explain it in terms of some elementary excitations which are now fermionic. So these are emergent excitations. So here it seems that the spin excitations, which are naturally expected to be bosonic, are somehow torn apart into two free fermions, two dispersing fermions, which I will call spin-ons following the literature. And so it's amazing that you have free fermion signatures in essentially a Mott insulator system. Okay, so today's talk is not about getting excited about spin-ons in bona fide spin liquids, but spin-ons when there are reasons to expect they should not be there. So here is one recent experiment on these cuprate superconductors. It is a measurement, it's a report on giant thermal Hall conductivity in the pseudo gap phase of cuprates. And what is seen is that for a very large variety of cuprates measured, if you measure the thermal Hall conductivity at relatively low hole doping, so you can have zero hole doping, for example, this example of LCO shows, or you can have 6%, 8%, this is a 20% doping. So you see that at high temperatures, there's not much of a thermal Hall, and these materials are magnetically ordered. It's a nail antiferromagnet in the parent state and at also small values of doping. As you decrease the temperature, what you find is that a significant thermal Hall conductivity develops, in this case negative, and they can go to pretty large values. If you measure it in terms of some quantum of thermal Hall conductance, it's order 1. It's a pretty big effect. So that's the surprise, because thermal Hall effect is expected to be rather small in a Néel state, and or insignificant. So what you have is a giant thermal Hall conductivity. At the same time, you have poor electrical conductivity. And you see it not only in the pseudogap phase, but also in the Néel state, meaning when you have a well-defined spin density wave order, such as LCO at zero doping. So clearly, since it is not in a conducting phase, it cannot be due to free carriers in the system. And it also is not due to magnons, because magnons ordinarily don't give us, magnons of a Néel state don't ordinarily give us such large uh, thermal Hall. Instead, the authors muse that it's quite reminiscent of insulating spin liquids and thermal Hall effects in those systems with topological order, such as alpha ruthenium trichloride, which is a candidate material for realizing Kitaev physics. So pretty soon after this, there was a Nature Physics paper from the Sachdev group, which gave a spinonic interpretation for this giant thermal Hall effect. So these spinons are emergent excitations, which persist apparently in the spin density wave ordered state. Okay, so now going closer to my topic of today's talk. This is about this quantized thermal Hall conductivity in alpha ruthenium trichloride, which apparently motivated this more recent work in cuprates. So now I'll spend a few minutes after this on Kitaev. But let me tell you briefly here that the Kitaev spin liquid state is uh, probably realized in this example on this slide. And normally, if it's a quantum spin liquid state, you should not have any magnetic order at low temperatures. But unfortunately, all material systems which have strong Kitaev correlations do order uh, at low temperatures, and alpha ruthenium trichloride is no exception. It orders in a zigzag manner. You see these hexagonal lattice which depicts the structure of alpha ruthenium trichloride sheets, and you can see the zigzag order is antiferromagnetic with same orientation on the zigzag edges of the graphene lattice. So it's not a spin liquid in the ground state, but you can try to kill it. So you can increase your magnetic field, and the Néel temperature falls. And ultimately, when you have reasonably small Néel temperatures, although it's not clear that it needs to vanish, uh, you begin to see very large thermal Hall conductivity. And it's quantized. And it's quantized at a value which is exactly half of what is expected for ordinary complex fermions, which means it's due to Majorana edge modes. So that's what makes it very exciting. And this is indeed a prediction from Kitaev's original work, which of course did not have any scope for magnetic order. It was a model of describing a Z2 quantum spin liquid. So let me then uh, give a few slides on what is important for me as far as the Kitaev model and its perturbations are concerned, and then tell you what I did. Okay, so Kitaev model is an Ising-like model. It looks deceptively simple with uh, with different kinds of Ising-like interactions on the three different types of bonds on a honeycomb lattice. So what you do is you put spin half particles at vertices of this lattice, and along the Z bonds, you allow the Z components of neighbors interact, and so on. And so while you might think that this might have lots of similarities with the Ising model in 2D, it doesn't. Um, and secondly, it turns out to be an integrable model. You can solve it exactly. It doesn't have any magnetic order, unlike the 2D Ising magnets. And as Kitaev showed, the quasi-particles are not spin-1 magnons, but they are gapped, localized Z2 vortices, which are pi fluxes essentially, and free Majorana fermions. So what are these vortices? Well, if you take any hexagon, say this one called W1, where I have labeled the spin coordinates 1 through 6, what you do is you take the spin 1 and an X bond is going out of it, so you write sigma 1X. Spin 2, a Y bond is going out of it, so you write sigma 2Y, and you go around the loop. So what you find is that these are conserved quantities. They commute with Kitaev Hamiltonian H. They also commute with each other, and they square to 1. So you can label your eigenstates with eigenvalues of W, and they can be plus or minus 1. So since in a system of n spins, there are n over 2 hexagons, this accounts for 2 to the power of n by 2 degrees of freedom. That leaves me to account for the remaining 2 to the power of n by 2 degrees of freedom. So to see that what these excitations are, which account for the remaining degrees of freedom, Kitaev wrote down the spin operators as a product of two Majorana fermions in this manner. And so Bx, By, Bz are Majorana fermions associated with the X, Y, and Z components of the spin operator. And C is Majorana operator, which doesn't carry any spin label, but all these B and C fermions carry site labels. And you impose a constraint at every site, which is that the product of all four is 1. So if you now put these representations in the Hamiltonian, you will essentially get a 4 fermion interaction. So here the details are hidden in this A hat matrix. But apart from the CICJ, you also have a product of B fermions here. But what Kitaev showed is that these operators Uij happen to be conserved quantities, and they commute with each other and they square to 1. But there are lots of these UIJs. At every site, there are 3 UIJs. And so in every, so since there are 3n over 2 links, that will give you 2 to the power of 3n over 2 possible combinations. But this is not, UIJs turn out not to be the physical degrees of freedom, because if it were so, then you have massively overcounted, because now given that you had 2 to the power of n by 2 flux configurations, and this is 2 to the power of 3n by 2, you will have 2 to the power of 2n degrees of freedom, which is square of the actual number. It turns out that physical quantities are these fluxes, which can be written in terms of these products of Uijs around the loops. So only those are the gauge invariant quantities. And once you do that, you have essentially solved the problem. So the elementary excitations are free fermions C, Ci, Cj, etc., and these plaquette fluxes, which can take values plus or minus 1. Unfortunately, real Kitaev materials, most notably alpha ruthenium trichloride and sodium iridate, they are antiferromagnetically zigzag ordered. And this is on account of small but significant competing interactions. So in addition to the dominant Kitaev interaction, you can have nearest neighbor Heisenberg. In addition, there could be further neighbor competing interactions which I have not written. There could be other types of nearest neighbor interactions which also compete, which are anisotropic in nature and can arise from just the symmetries or from various kinds of deformations of the crystal. I won't go into too many of these details, because my job is today not to explain these materials, but study a toy model which just has Kitaev and the nearest neighbor Heisenberg interaction. Kitaev I take to be ferromagnetic in sign, and J to be antiferromagnetic in sign. For this simple model, the phases are well known. If the Kitaev interaction is dominant, so here's an axis which is J by K. So as long as Kitaev interaction is dominant, the ground state is essentially that of like a Kitaev spin liquid, despite the presence of these perturbations. If the J by K exceeds 1 by 8 and up to 0.75, you have a ground state which shows stripy order, and beyond you have nail antiferromagnetism, where the physics is dominated by just this first term. Somewhere in the middle, when J by K is 0.5, the stripy state is an exact eigenstate. And these guys showed that you can do a sublattice transformation and map the stripy antiferromagnet, or the model in fact, to a pure Heisenberg ferromagnet. So that means the ground state is an exact eigenstate and it's a direct product state. Okay, so coming back to my motivating slides, my question is, can the exact many body excitations of the JK model resemble Kitaev quasiparticles better than magnons, even in the stripy state? So there are two scenarios. One is like, should I look at the excited states? Because the reason is that the dominant interaction in the model is still Kitaev. And once the zigzag order is destroyed by, say, raising the temperature, shouldn't the high energy excitations involved be better described by just the Kitaev term in the Hamiltonian? The counter view is that the low energy excitations of a 3D magnet are spin 1 bosons and not Majorana fermions. And this system is magnetically ordered in the parent state. So if you look at higher energies, magnon-magnon interactions become important and cause the magnon decay. And you also have residual Kitaev interactions in the magnetically ordered state. They may further enhance magnon decay, but all this is within the ambit of interacting spin wave theory. Um, then you can look at instead ground state and low-lying states by either magnetic field tuning or other means, and ask if these states are have any chance of resembling the Kitaev excitations, just like it was the case in the
Hello.
Sorry, can you hear me?
Yes, yes,
Yeah,
yes,
it got disconnected for a moment.
yes,
Yeah.
yes. Because
Okay. So so experimental evidence is there to support both views, and one set of data I want to show here is inelastic neutron scattering. So on the left panel you see some curves which are basically your scans in energy, and you measure the intensity of inelastic neutron scattering at fixed wave vectors. So these peaks are essentially due to whenever there is a E versus Q dispersion satisfied, then you, i.e. a magnon, you expect a peak here. And so you see that at low temperatures, you see very clear peaks in the magnon dispersion, which are sign of magnons. But as you go above the male temperature, you see complete smearing out of these magnons. So,
so you have 4 minutes left,
actually,
Vikram.
yeah. So you see a similar trend if you scan in momentum but fix the energy. You see that at low temperatures the magnon signal is there, but at higher uh, energies or higher temperatures the magnon signal goes away. And so the belief is that as you go to higher energies, then your Kitaev quasiparticles are probably the likely stable quasiparticles, and you are seeing an effect of that in the form of very incoherent features in the inelastic neutron scattering. Okay, so we also did some investigations of the other Kitaev material around that time, and it was published last year. So what we found is that high field magnetometry shows these non-monotonous features, which are incidentally seen in alpha ruthenium trichloride also. And using these, we arrived at a model with very constrained parameters. And if you now calculate spin-spin correlation functions as a function of distance, you find that as you increase the magnetic field to suppress magnetic order, uh, the spin-spin correlation functions begin to fall very fast with distance, whereas if you are at low magnetic fields, you have magnetic long-range order, then the spin correlation functions decline very slowly with distance. Okay, so to pose today's problem, are stable K-type quasi-particles possible in the stripy phase? If not, do stripy magnons better describe the many body excitations? And if yes, should one look at low energy excitations or high energy ones above the magnetic ordering scale? Okay, so now the story is that I want to pose it as a problem of Fock space localization. So before that, what's the physical meaning of a quasi-particle lifetime? Well, I want to regard any quasi-particle as an approximate excitation in the system, approximate eigenstate of the system. You can always write it as a linear superposition of exact eigenstates of the problem. And these eigenstates can be exponentially large in number in general, okay, in system size. If you evolve this state in time, then individual components acquire different phases because the energies are different, and two nearby energies, sorry, if two components are separated by an energy delta E, they become phase mismatched at a time order 1 over delta E. So if the energy levels are exponentially close, then this phase mismatch time for nearby states diverges with system size exponentially in the thermodynamic limit. However, if the support size of this state, i.e. how many CNs are actually significant, suppose the support size in Fock space consists of a macroscopic fraction of many body states, then the fidelity becomes small in a finite time, even in the thermodynamic limit, and the particle is said to have decayed or become unstable. Okay, so this is the idea which was first proposed for quasi-particle stability analysis by Altshuler and others in 97, and mapped it to a problem of Fock space uh, support. So the idea is to compute the inverse participation ratio and calculate the support size of Kit-type states in the Fock space of exact states of the JK model. Then look at the scaling of the support size as a function of the number of spins. So if the scaling of the support size is like the Hilbert space dimensionality, then the Kit-type state is unstable and it's not a good approximation to the exact eigenstate. Um, if it scales like fractal with C less than 1, then the Kitaev state is stable even though it's delocalized in Fock space. And if the support size scales weaker than exponential, then the Kitaev state is completely stable, and it's an example of many body localization. No disorder here. Okay, now the problem is to describe the delocalized states, we need an exponentially large number of exact eigenstates. And this is what Carlos described as my exponential barrier. So there are various strategies to compute intermediate excited states, but they are not very good. And there's a new kid in town called Feast. It's a contour integration based algorithm. It yields eigenstates in arbitrary user specified eigenvalue ranges, and it allows parallelization at multiple levels. So this is the one we are going to use, and I'm not going to have the time to describe this strategy in more detail, but you can ask me later. But what we found is the following. So suppose I try to look at the Fock space scaling, support size scaling in Fock space by this ansatz and do finite size scaling fitting. I find that if I look at low-lying K-type states and I start increasing the value of j by k, I find that when j by k is small, the scaling, the support size is more or less unchanged as a function of n, and this scaling gives me a quantity with positive slope and an intercept which is close to zero within error bars. And once I go to higher values of j by k, a finite C emerges, approximately coinciding with the boundary of spin liquid and SDW order. And then once I reach the peak of stripy order, the coefficient C becomes 1 and the state becomes fully delocalized in Fock space. So so I would say it is here that the Kitaev state becomes unstable. And if you simultaneously look at what is happening to stripy magnons, you find the opposite story, that the magnons are remarkably stable in the vicinity of the peak of stripy order. But as you start reducing your Heisenberg interaction, the magnons start getting destabilized. I'm showing here a region around the peak of stripy order. Just as Kitaev states have got delocalized, magnon states are actually localized. Okay, so then the question is, what's better? Magnon excitations of the stripy phase, say at J by K is 0.5, or Kitaev? Well, it depends on the energy window as well as your perturbation. So if you look at small Kitaev perturbations, I'm already in the stripy phase here, by the way. What I find is that nevertheless, the Kitaev support size is smaller, and both states support size is shown here. This is for Magnon, this is for Kitaev. So Kitaev provides a good description. If I increase my perturbation, both are roughly good at intermediate energies. At low energy densities, Kitaev is still better. If I go closer to the peak of stripy order, it's clear that Magnons are better, and Kitaev becomes a bad description. Okay, so using these, I construct a finite temperature phase diagram. So on the vertical axis, I show temperature. On the horizontal axis, my perturbation J by K. So if the perturbation is small, I am in the Kitaev phase. If the perturbation is large, my ground state is magnetically ordered. But this is the line which is the computed Néel temperature from specific heat calculations. And this curve is basically the cost of introducing a vortex, a pi flux in the system, which is about 5% of the Kitaev interaction in the Kitaev phase. And it doesn't, funnily enough, disappear abruptly as you enter the magnetically ordered state. This line is new, which is obtained from MBL calculations. It tells me like where exactly Kitaev quasiparticles are stable. So the claim is that they are not stable above this, and below they are stable. So if you look at this region, you find that there is a region above the Néel ordering temperature where Kitaev quasiparticles are stable. But in general, your chances are better to find stable Kitaev quasiparticles in the magnetically ordered phase, in fact. So this magnetic order is, in my opinion, a red herring. It's like ripples on an ocean, and the real nature of the wave function is Kitaev-like more than it is Magnon-like.
So Bikram, maybe you can wind up. We
Yeah,
are
okay.
actually
So here's my conclusion. So spin-ons are elementary excitations in numerous spin liquids, and spin-on effects in magnetically ordered phases is a very interesting topic currently. Real Kitaev materials are known to be magnetically ordered, and so it's important to understand if Kitaev properties may be realized in these systems. We studied the stability of Kitaev quasiparticles in the presence of a perturbing Heisenberg interaction as a Fock space localization phenomenon, and delocalization in Fock space implies quasiparticle instability. A finite temperature calculation show that a vortex gap and a non-zero Wilson loop at low temperatures, which are both characteristic of the deconfined Kitaev spin liquid phase, persist far into the neighboring phase that is magnetically ordered. And the field dependence of entropy, which I didn't have time to discuss, is very similar in the KSL and PSL phases, and it's quite different from that of the direct product magnet. Kitaev quasiparticle excitations are stable at low energies over a significant parameter range in the stripy phase. The Kitaev stability line encompasses areas both above and below Tn, so it's a different curve altogether, with the former only possible in the vicinity of the KSL PSL phase boundary. Thank you for listening to me. Bye.
Yeah, thank you very much, Vikram. So since we are running short of time, we have two quick questions, one from Arnav and then one from Subroto. Maybe Arnav can ask the first question. Arnav Sen, please.
Yeah. Hi, Vikram. So I have a question. So in your calculations, you use the subdominant term to be the Heisenberg interactions, and then you sort of argued for the stability of the Kitaev quasi-particles. Is
Yes.
there a more general way of thinking if, let's say, I perturb the Kitaev model with some other term, right? Not just the
Sure,
Heisenberg.
sure, sure. We
So,
have actually tried but not reported lots of different models which are used for Kitaev, meaning those with gamma gamma prime type of interactions, as well as further neighbor Heisenberg interactions. And especially for the gamma gamma prime thing, the results are quite interesting. It seems that for large gamma, so suppose you have a K gamma model, forget gamma prime. There is the large gamma model itself is interesting. It shows a non-zero plaquette Wilson loop whose value is minus 0.3 instead of 1 for Kitaev. And so it looks like another one of those deconfined phases, which is not Kitaev-like.
I see.
You can destabilize it by adding a gamma prime term and make it undergo a zigzag ordering. So here, in fact, large gamma creates its own kind, seems to be creating its own kind of different deconfined phase. I think there have been other sets of works by probably the Yongbai Kim group, which have claimed in some different ways that large gamma dominated term is probably a different kind of spin liquid. So my unpublished findings seem to be supporting that claim.
Okay, I see. Thanks.
So, Subrato, maybe you can ask a question.
Yeah, thanks, Tapan. Nice talk, Vikram. I actually had a question about the thermal Hall conductivity that you mentioned in your early slides. So, so the thermal Hall conductivity that you were talking about in these materials, is that quantized or is that unquantized? Because I thought that if it is quantized, then it's really a signature of there being chiral edge modes, right? On the
Yes.
other hand, if it's unquantized, then I suppose you're not really talking about chiral edge modes. But then why do you have to look at the thermal Hall conductivity? Why don't you just look at the regular thermal conductivity? Is that because that's masked by phononic effects or something?
That's right. And also in alpha ruthenium trichloride, the thermal Hall is quantized, and it's got that half integer quantization, which tells you that not only there are chiral edge modes, but they're also Majorana in nature. In cuprates, the thermal Hall conductivity is order 1, and it cannot be easily accounted for in terms of a simple Magnon picture. The longitudinal conductivity is clouded by phononic effects. And so you have to, it's a difficult task separating that out. But I believe that if one manages that, then that also should be quite an interesting quantity to look at.
Thanks.
Okay, so let us thank Bikram once again, and then maybe we'll move on to the next talk. Thanks, Bikram. So the next talk is by Professor Pinaki Sengupta from NTU Singapore, and the title of the talk is Antichiral Magnon Edge States in a Heisenberg Ferromagnetic. So Pinaki, yeah. Yes. Hello.
Hello.
Oh, okay.
Yeah.
Sorry about that.
No problem.
Okay. Good morning, everyone. I would also like to start by thanking the organizers for organizing this conference under these unusual times and giving me the opportunity to be a part of this 50th year celebration of DST and share some of our recent results. The pandemic has brought online conferences and meetings mainstream, and I agree with Professor Shomit, who said that in the long run, the community will benefit from this paradigm shift. But today I will talk about antichiral edge states in a honeycomb ferromagnet. This is work done by Dhiman, who just completed his PhD with me. It's a short story and I will go slowly. I will start with a brief review of the Halden model and chiral edge states. That will give me a natural context to introduce the Halden model for magnons, which will lead to the breaking of time inversion symmetry and how that leads to antichiral edge states. We will see how time inversion symmetry is broken and how that gives rise to antichiral edge states. I will then discuss some experimental signatures of antichiral edge states and end with some speculative musings about material realizations. The Halden model was introduced to demonstrate that quantum Hall effect can arise even without strong magnetic field and Landau levels. Although most of you are familiar with the Halden model, I will review it briefly because that will prepare the groundwork for me to introduce the antichiral edge states. It consists of standard block band structure with broken time reversal symmetry, but zero net magnetic flux through the system, which means that breaking time reversal symmetry breaking is essential for quantum Hall effect, but not a net magnetic field. This produces a Chern insulator, which is a precursor to time reversal invariant topological insulators of Kane and Meili, which can be thought of as two copies of the Halden model. The starting point is the tight binding model of spinless fermions on a honeycomb lattice. In other words, spin polarized graphene. In the absence of any spin orbit coupling, introduction of spin degrees of freedom does not introduce anything extra, just produces two copies of the band structure. There are two bands consistent with two side bases, which cross linearly at the Dirac points. The Dirac points are protected if both inversion and time reversal invariance is present. Here, I want to highlight that for the purposes of this talk, I will assume inversion, symmetry, and sublattice symmetry to be the one and same. And oh, by the way, there is this online course on topological Cordes matter, and in this particular website or particular page, there is a short video by Halden where he explains his model. And in this short 8-minute video, he presents the most elegant and succinct summary of his model. It's highly recommended that you watch it. So that's graphene. Now, Halden introduced topological character to this model by introducing a complex second neighbor hopping. So you have a complex hopping between sites on the same sublattice, but now with a complex hopping amplitude, which is T2 times e raised to the power I5. So the hopping amplitude is T raised to the power T2 times e to the power I5 if the hopping is in a counterclockwise direction, and minus I5 if it's in a clockwise direction. Here, I want to point out that the hopping, the complex hopping is identical for the two sublattices. That is, if it's plus I5 for counterclockwise hopping for A sublattice, it's the same thing for B sublattice. This will become important later when I introduce antichiral edge states. Forward and backward hopping processes are not equivalent. So in other words, a hopping from along the counterclockwise direction and counterclockwise direction are come with complex hopping amplitudes which are complex conjugates of each other. This breaks time reversal symmetry. Time reversal symmetry is broken without breaking inversion symmetry, and that opens up a gap at the Dirac points. The two bands are shifted symmetrically at the two Dirac points. And the bulk bands carry non-zero Chern number. So to summarize, complex next nearest neighbor hopping opens up a gap at the Dirac points. The two bands are shifted symmetrically at the two Dirac points. And at the boundary of since the bulk bands carry non-zero Chern number, at the boundary of a finite system, there is an interface with a topologically trivial system, which is the vacuum, and a topologically non-trivial system, which is the bulk of the system. So there are there exists, the energy gap has to vanish, and that is accompanied by gapless edge states. So if you have the gapless edge states in this particular case, for this particular edge geometry, connects the K point of the lower band with the K prime point of the upper band, and vice versa. If you have the Fermi energy in the gap, then one of the edges or one of the gapless edge states come with a positive slope, where the other comes with a negative slope, which means that there are two counter propagating edge states along the two edges of a infinite stripe geometry or ribbon geometry. The edge states are protected by chiral symmetry, which means that there is no scattering between the edge states and the bulk states. The bulk remains insulating, whereas there are these chiral edge states along the edges. Now, while the model is interesting, it sounds unphysical. In fact, Holden, in his paper, marked that although this is unlikely to be physically realizable, etc., etc. Now, it's true that it has been realized in recent cold atom experiments, but it's fair to say that it sounds unlikely that this will appear naturally in a material. And this is where quantum magnets come in. Quantum magnets have for long been a versatile platform to realize complex bosonic phases, for example, BEC of magnons. And that's what we will use here. Magnons are low energy excitations in a quantum magnet. Again, this is more of a pedagogical talk. So it's useful to have an intuitive picture of a magnon as a flipped spin in a background of a ferromagnetically ordered ground state. Now, of course, you know that an effective picture would be to describe the magnon as a quasi-particle moving in a vacuum of the background ferromagnetically ordered ground state. Now, for a Heisenberg ferromagnet, you know that the correct low energy excitations are spin waves, but there also you can the spin waves for different crystal moment K act as independent quasi-particles, and they are the magnons of the system. The magnons obey Bose-Einstein statistics, and importantly, they can be generated by thermal excitation or an external magnetic field. This is what makes them so versatile to controllably generate complex bosonic phases. And many such phases have been realized in the past, and more recently, bosonic analogs of topological phases have been proposed in quantum magnets. In particular, bosonic analog of the Holden model appears for magnons in a realistic Hamiltonian for quantum magnets. To start with a Hamiltonian for interacting spins on a honeycomb lattice. Now, this has gained popularity in recent times following the discovery of a large number of honeycomb ferromagnets such as chromium trihalides, transition metal phosphorus trichalcogenides, and others. This is the Hamiltonian describing, generic Hamiltonian describing honeycomb ferromagnets. The first term is the Heisenberg interaction, which favors parallel or anti-parallel spin alignment depending on the spin sign of J. Here we will consider parallel alignment. The second term is the Giallo-Schick-Moria interaction, which favors perpendicular spin alignment. And it's the interplay between these two interactions that give rise to a large number of complex magnetic phases. The DMI is ubiquitous in many quantum magnets and arises from spin-orbit coupling. The nature of DMI is constrained by the symmetry of the lattice. For a honeycomb lattice, the most common DMI is on next nearest neighbor bonds. It's a vector which is normal to the plane and acts on next nearest neighbor bonds. For this form of DMI, the spin Hamiltonian reduces to a Heisenberg term and the DM term, and this is the Z-band term from an external magnetic field. The ground state of this Hamiltonian has ferromagnetic ordering for d less than j over square root of 3. Okay. Hello? Yes? Hello?
Yes.
There is some, I thought I heard some comment or no?
No. Okay.
Shall I go on?
Carry on.
Okay.
Yeah.
Thank you. Thank you. Now, this model was introduced in a paper by Yaroslav Sarkovniak in 2016. Now, what we will do is consider magnon excitations above the ground state. Okay, to do that, we will use the Holstein-Primakov transformation, which maps the spin flip operators to creation and annihilation operators of Holstein-Primakov bosons. In this expansion, we will keep only the leading order term, which is effectively using the linear spin wave theory. The magnons are the Holstein-Primakov bosons created by these AI dagger or these bosonic operators. Now apply the Holstein-Primakov transformation to the spin Hamiltonian, right? That is, write out express the spin Hamiltonian in the language of these Holstein-Primakov bosons. This will result in a large number of terms of degree 2 to 4. What we will do is keep terms only up to bilinear in AI dagger or AI, the creation and annihilation operator. We will treat any higher order terms in a mean field approximation. For example, the Ising term will result in a quartic term in AI dagger. What we will do is reduce it to a bilinear term using the mean field approximation. In this limit, the effective magnon Hamiltonian reduces to that of a time-binding model of magnons on a honeycomb lattice with nearest neighbor hopping with hopping amplitude Js and the next nearest neighbor hopping with a complex hopping amplitude and a chemical potential term that controls the total density of magnons. So importantly, the next nearest neighbor hopping is exactly of the form that was used by Haldane in his model, with the hopping the phase of the complex hopping term being phi equals pi by 2. Now, since the energy dispersion of a time binding model does not depend on the quantum geometry or quantum statistics of the particles, namely whether it's bosonic or fermionic, the energy bands are identical for the energy bands for the magnons in this model are identical to that of the Haldane model. Namely, you have two bands which which will be degenerate at the Dirac points if there were no DMI present. That is, for d equals 0, the bands are degenerate at the Dirac points, k and k prime. For d greater than 0, the two bands shift symmetrically apart. Once again, I emphasize the point, they shift symmetrically apart and the band opens up at k and k prime. Once again, the bulk bands are gapped and carry a finite non-zero Chern number. So that in analogy with its fermionic counterpart, chiral edge states appear in a finite system. They are protected by chiral symmetry. It consists of counter-propagating spin current along two edges of a Riemann geometry with zero net spin current in the bulk. Now, what I forgot to mention here is that this chiral symmetry protection makes it robust against any local perturbation such as impurity. So if there are any impurities, that does not suppress the edge states. Okay, that's all nice and good. But what happens if I break the sublattice symmetry? In other words, I have the two sublattices are different. Now that can happen for either by having two different atoms on the two sublattices, which happens, for example, in hexagonal boron nitride. But in a magnetic material, that's rarely the case. It's usually the case that in a magnetic material, one of the ions carry the magnetic moments. For example, it's chromium in chromium trihalide compounds, it's iron in FePS3, manganese in MnPS3, and so on. The magnetic moment carrying atoms form the honeycomb lattice, or are arranged in a honeycomb lattice configuration, forming the magnetic lattice. But the presence of multiple other ions can result in a different local environment for the two sublattices. This is realistic in uh, a quantum magnet. So if the two sublattices are inequivalent, then the DM interactions are different for the two different sublattices. And that makes things make the situation much more interesting. So if the DM interactions are not equal on the two sublattices, I can define a symmetric and antisymmetric combination of the DM interactions as D and D prime as dA plus dB over 2 and dA minus dB over 2. With this, the Magnon Hamiltonian is now modified to the following, where you have the regular Halden model for the Magnons making up the first two terms. The third term is the interesting part. This is again a next nearest neighbor hopping with a complex hopping amplitude. But now, oh, I'm sorry, I am missing a I here. So there should be an I here. So it's I times d prime s times nu prime ij, which means the following. Now the complex hopping is opposite for the two sublattices, which means that if the complex hopping term comes with a plus I for counterclockwise propagation of Magnons or on one sublattice, it comes with the same sign for clockwise propagation of the Magnons on the other sublattice. And that breaks the inversion symmetry, which I said I will not differentiate from sublattice symmetry breaking. Now, this an analogous model was proposed for fermions by Franz and Colomes back in 2018. But once again, that is not a natural term in fermionic systems, whereas this is quite natural in a quantum magnet. So for in the presence of this d prime term, the two bands are now shifted anisotropically at the two Dirac points. And this is why I have been emphasizing symmetric separation of the bands for the regular Halden model. The
Pinaki, you have,
yes?
You have 5 more minutes.
Okay, thank you.
Yeah.
So the magnitude of the band gap at each Dirac point, which is the difference in energy between the two bands at the same Dirac point, is proportional to the symmetric DM interaction, and this asymmetric shifting of the bands results in a band tilting. The tilting of the bands is defined as the difference in energy between the same band at the two Dirac points. And this tilting is proportional to D prime, which is the anisotropic DM interaction. Now, for a finite system, the edge states acquire similar dispersion. This is a heightened or an extreme case where we have assumed D to be 0 and D prime to be finite, which means that the DM interactions are equal and opposite in magnitude, equal in magnitude and opposite in sign for the two sublattices. That's an extreme case, but in that case, this is the scenario that you have this two bands or the two edge modes coinciding with each other, joining the two Dirac points. In a more generic situation, there will be a band gap opening. There will be some finite D, some finite D prime, which will make the two the two dispersions at the two edges to be different. Okay, this results in a slightly different scenario from before. First of all, the inversion symmetry breaking breaks the chiral symmetry, protecting the edge states. Now scattering between edge states and bulk states is allowed. As I said, for D prime much greater than D, the dispersion is similar for the two edges, which means that there will be co-propagating spin currents along the two edges. And these constitute the antichiral edge states. That is, the spin current along the two edges is in the same direction. To conserve spin, to keep the net, to conserve the net spin current, is the spins along the edges is balanced by a counter-propagating bulk current, which is allowed by this chiral symmetry breaking due to the asymmetry between the DM interactions of the two sublattices. And if you measure the currents, it has a profile like this. This is the spin current along a cut along the ribbon, and this is the magnitude of the current, which is along the same direction at the two edges and in the opposite direction in the bulk. So there are, once this is realized in an experiment, what are the experimental, or in a real material, what are the experimental signatures? One is definitely you can use neutron scattering to directly probe the band dispersion. You can use magnetic force microscopy to zoom in and measure the spin currents at the two edges separately. But there are also other experimental signatures like probing the spatially resolved low energy excitation spectrum reveals distinct signatures of asymmetry between the two edges. Here, we have chosen a case where one of the dispersion is 0 or flat, and the other has a dispersion which arises when one of the DM interactions on one of the sublattices is 0. So that one of the bands is flat, which means that there is no spin current along one edge, whereas there is another net spin current along the other edge, which results in a distinctive dynamical structure factor at the two edges, which can be probed in a realistic experiment. Since I am running out of time, let me just conclude with some speculative musings about material realizations. One feature of these new materials is that they are bound by weak interlayer van der Waals coupling, which means that it's easy to form layered heterostructures with tailored properties. In particular, if we can break the inversion symmetry in a compound like chromium germanium tritelluride, which consists of germanium atoms at an apical position in the middle of the honeycomb lattice, and replace alternate germaniums by silicon, then we can show that the local environment at the two sublattices will be different, which can result in antichiral edge states. So let me conclude the Holden. Well, I will let you read through the conclusions. And before I And let me stop here and if, take any questions that you have.
Okay, so thank you, Pinaki, for that nice talk. And we have two questions, one from Indra Das Gupta and one from Subrata Mukherjee. So, Indra, maybe you can ask your question.
Yeah, Pinaki, very nice talk.
Thank you.
So I would like to ask, you have a Heisenberg interaction and a DM interaction.
Yes.
And as you correctly pointed out, for a honeycomb system, DM interaction is second nearest neighbor.
Right.
I think in such kind of systems, in a honeycomb system, you can always have a first nearest neighbor Kitaev exchange. So for example, if you have a Heisenberg plus a Kitaev,
yes.
Is anything known about such a system?
I do not know that. I do not know
Am I
that.
audible?
Vikram, yeah, you are audible. I have not studied the effects of Kitaev interaction. We briefly looked at other interactions like single ion anisotropy.
Am I audible?
Yes, you are. Can't you hear me? Did I mute myself again? No, I am on.
Hello?
Indro, can you hear me?
Yes. Pinaki, can you hear us?
Yes. Can't you hear me?
I'm not able to hear Pinaki. We are not.
We can hear both of you actually.
Yeah,
Pinaki, I cannot hear you.
I can hear both of you as well.
Okay, I can hear Indro, but for some reason he cannot hear me.
It's not able to hear anyone, I think.
So let me reply via chat, Indro.
Hello?
Yes?
Yeah, did you hear my question?
Yes, okay.
Now.
Okay, no, we have not studied the effects of Kitaev interactions. We did study the effects of single ion anisotropy or even nearest neighbor DM interactions. None of those changed these qualitative features of the results. But I agree that having Kitaev interactions or studying Kitaev interactions will be interesting.
Okay, thank you.
Subrata?
Yeah, nice talk, Pinaki. So my question has to do with the fact that you actually have a bosonic model here, right? Instead of a fermionic model.
Yeah.
So now in a bosonic model,
yes.
how would I think of these, edge excitations as being low energy excitations?
Right. Very good question. Very good question. Remember, Subrata, I paused for a moment at the conclusion. This is what I wanted to say. Okay, so here's the thing. So despite all my tall claims, why haven't people observed topological phases of magnons recently? Although you have Bose-Einstein condensation of magnons, analog of Mott insulators in magnons, why not topological phases? The reason is the following, that bosons do not obey Pauli exclusion principle. So although we can populate with bosons, we cannot fill up to the Fermi level.
Right. So you won't get a churn insulator, for instance, with
except for the fact, okay, the other thing is that the Berry curvature is localized near the K points or the Dirac points. So these are the Berry curvature hotspots. Whereas the magnon density is concentrated normally at the gamma point at low temperatures.
Right.
That is the main bottleneck. So there are two ways that we are thinking, we are now considering, we are studying now. One is to use a circularly polarized light to excite magnons at selected momentum, namely close to the Berry curvature hotspots.
Right.
That will let me probe directly the Berry curvature hotspots. The other one is to, in some cases, for example, in the Shastri-Sutherland model, we are showing that we find that if you apply an in-plane magnetic field, then the Berry curvature distribution in the magnetic Brillouin zone will be redistributed, and for some combination of fine-tuning of in-plane and out-of-plane magnetic field, we can bring the Berry curvature hotspots to the bottom of the band, which means that there you will see the effects of topological effects of magnots. Does that answer your question, Subroto?
Yeah, thanks.
Yeah. So we have one last question from Professor Diptiman Sen. Maybe you can ask your question.
Yeah. Hi, Pinaki. Very nice talk.
Hello. Thank you, Diptiman.
Yeah. So actually, these edge states can give rise to effects like a thermal Hall effect, right?
That is true. That is true.
And I think people have measured that in some systems.
Diptiman, the only place I know is this LU2 V207, which was measured a long time back by a Japanese group, but not for these two-dimensional materials like chromium, triiodide, or strontium copper borate, where people have failed to measure.
Okay.
I believe that is because of this issue of when you excite magnots, it's always at the bottom of the band, and whereas the very curvature hotspots are far away.
Right. Right. Yeah. Okay. Fine. Thank you.
Okay. So one last question, maybe Brijesh Kumar.
Hello, Pinaki.
Hi, Brijesh.
Good to hear. Nice talk. Just a query about the two co-propagating edge modes that you mentioned towards the end of your talk.
Yes.
I mean, if you have cylindrical geometry, you are saying the two guys are moving in the same direction, compensated by a bulk current, which is in fact a very significant effect that they are inducing a current in the bulk.
Brijesh, just one quick correction. I'm not thinking about a cylindrical geometry. I'm taking a ribbon, plain stripe.
Ribbon.
Yes.
Okay. Okay.
So the bulk is the body of the ribbon, and edge is the literally the line cutting the
then my question then is that which side of the I mean, ribbon is not closed. You mean it's like a rectangular
it's infinite
geometry?
Ribbon.
Is that what?
Yes, it's infinite ribbon.
Infinite ribbon. Okay.
Yeah. Yeah.
I don't know. I mean, suppose if it was a finite rectangular geometry, which
right.
edge does it select it to propagate? I mean, it looks like there is nothing at the edges. I mean, sorry, but this is what I felt, that if you have a rectangle,
yes,
then which two sides are the edges?
Okay, that will Brijesh, that will depend on which direction you. Okay, here I am implicitly assuming.
I mean, my only worry is that in just one second. Sorry, I'm interrupting, but my only worry is in a genuinely open geometry with all four edges being open.
Yeah.
They might just end up canceling each other. So I don't. This is what I thought. Maybe you have done the calculation. You have better insight.
We have done the calculations for an infinite stripe. But you are right that for a finite rectangle with comparable sides, things will become very non-trivial. It will depend on where I excite in which direction I excite the initial background mode. So there you will need some excitation to initiate the background modes, and that will depend. Although there is the scattering between bulk and edge states are allowed, it will still be not. It will not be persistent, but it will have an algebraic decay.
Okay. So sorry to interrupt. Shall we to the private platform? Maybe we have to continue now.
Sure.
Yeah. Thank you.
Thank you, everyone.
Yeah, and let's thank Pinaki again. So the next talk is by Dr. Arijit Datta from HRI Allahabad, and the title is A Novel Approach to Out-of-Equilibrium Dynamic Hubbard Model. So Arijit, please share your screen.
Yeah. Hello, can you see the screen?
Yeah. Please go ahead.
Okay. Just hello, good morning, everyone. I would start with thanking the organizers for giving me this opportunity. So I'll give a motivation for this work, and then I'll briefly go into the formalism, discuss the results, and then conclude. So the motivation for this work comes from experiments in Mott insulators, which are driven out of equilibrium by applying a voltage bias. We find that across materials, there seems to be this qualitatively similar current voltage characteristic. So the IV characteristic is discontinuous at low temperatures, shows hysteresis, and the coexistence region persists up to some temperature, T coexistence, after which it shrinks and the characteristic becomes unique. It loses the sweep dependence. We also see, we find that such similar behavior occurs across different length scales, which you can see from here, right from nanometers to a few millimeters. So, so we want to explain this kind of first order transition in Mott insulators, and we also want to study the temperature dependence of the IV characteristic. So most existing techniques, the most existing theoretical techniques are either limited in size or time. Although DMFT can access lattice problems for moderately long times, but it does not get the correct transport characteristics. We'll come to that later. So we want to capture the steady state, static and dynamic correlations, and we need a finite temperature scheme which is non-perturbative in U to capture Mott physics and the applied voltage V to access insulator metal transition. And we also want a real space and real time formulation which is necessary for treating spatial inhomogeneity due to breaking of translation symmetry as there is an applied bias. And we also want access to dynamical correlations. So we start with this driven dissipative Hubbard model, which has been shown schematically here. So this central region is the system which is modeled by a repulsive Hubbard model at half filling. So, and the leads are non-interacting, and these are coupled by tight binding coupling. The bias enters the story by, through chemical potentials in the leads, which are maintained at plus minus V by 2, V being the bias. And we work in 3D in the cuboidal geometry, where this transport direction is longer as compared to the transverse directions. And we impose a periodic boundary condition in the transverse directions. So to proceed, we have to model the system and write a real-time Keldysh action by discretizing this complex time contour. So then we decompose this interaction term into auxiliary fields, the phi, the charge field, and m, the spin field, and then integrate out the electrons. This gives an effectively non-interacting problem. So it maps the original problem into an effectively non-interacting problem for the electrons, but the electrons now sense a time-dependent background. Then we expand the action in difference fields. So this Keldysh technique leads to doubling of degrees of freedom. It also leads to doubling of the auxiliary field degrees of freedom. And you can take linear combinations of these to define some average and difference fields. So we expand the action to second order in difference fields, and but retain the average fields exactly, which gives you, for example, correct mean field theory at 0 temperature, because you retain the average fields exactly. So, and then we introduce a noise by doing a Hubbard-Satanovich transformation of the second order term in the difference field. We further assume that the spin dynamics is slow. In other words, the dynamics of these M fields is slow. And as compared to the electron, we go to center of mass coordinates and relative coordinates, and then do a gradient approximation in time to order h bar, but we treat the spatial coordinates exactly. Finally, we integrate over the fast electronic coordinates. So all this mumbo jumbo leads to this set of coupled problems, two coupled problems, where the electronic dynamics is governed by this Hamiltonian, which is essentially a free electron problem in a time-dependent background. Hello? Hello? Hello?
Yes, we can hear you.
Right, okay. So the electronic problem gets mapped to, so the original problem gets mapped to two coupled problems, where the electron dynamics is controlled by this essentially free Hamiltonian with a time-dependent background. This background evolves according to an effective Langevin equation, which gets a feedback from the electrons through these sigma averages. These are the instantaneous electron spin expectation value, and the bias enters the story through these averages, and the noise driving this equation is assumed to be classical. I mean, although it depends, it is very non-trivial, but you can invoke this high temperature limit. So where the temperature is much larger than the Magnon excitation energies, and to simplify the noise to this uncorrelated form. In this form, it looks additive, but it is actually the noise is multiplicative. So using all this, you get on solve this equation. So the scheme is twofold. First, you solve this equation, and for each instant of time, you compute the electronic average and feed it back into this equation and evolve. So on solving this equation, you get a time series for m's. To get a feel for what's happening, you can compute the nearest neighbor averages, fine. So, and you see that so this is at equilibrium. If you plot it at for different temperatures, so at low temperatures, it's supposed to have antiferromagnetic Néel order, and you see that this is large and negative, and there are very tiny fluctuations. As you increase temperatures, the mean value remains spin, but the fluctuations start to grow even before the system loses order. Now, when the system loses order, the mean value goes to 0. But even before that happens, you see that there are large fluctuations in this object, which goes to show that the order is lost due to slow but large fluctuations of these moments. So before I go to show my own results, I would like to briefly go through what happens for the equilibrium Hubbard model on a square lattice. So on the square lattice, it's an antiferromagnetic insulator at low temperatures, and it's a Mott insulator for large U by T, U by T greater than 6 or so. It is, and that is also backed up by the fact that the Néel temperature goes as T squared by U at large U, whereas it goes as some Hartree-Fock form for small u. Now, if you are above this antiferromagnetic region in this paramagnetic phase, above this red line, you find that there is a metal to insulator crossover in this phase, but no such thing happens if you are at large U. There is no insulator metal transition or crossover if you are at large U and hitting the system. Okay. So we want to know what happens to these equilibrium scales. There is a pseudo gap scale which forms when you heat the system at large U, and there's also this Néel temperature scale. We want to know what happens to these scales when you put a bias.
So Arijit, you have 2 more minutes.
Okay, so the answer is this. We have, this is the phase diagram. We see that the Néel temperature collapses as you increase the bias, and there is a new scale IMT, which is the insulator metal transition scale, which was not present at equilibrium but emerges strongly out of equilibrium. We also find that the current voltage characteristic has this distinct first order transition. Depends on whether you are increasing voltage or decreasing voltage, and it is markedly different from the form predicted by other theories like DMFT, which would give you such a form. So to delve into it further, we can do a detailed inspection of the IV characteristics to infer the regions, the metal insulator transition. So I'll not go into the detail, but just emphasize that this looks very similar to the experimentally obtained IV characteristics. And further, we can calculate the DOS, and we see that the pseudo gap scale collapses as a function of bias. And the entire physics is captured, essentially governed by what the magnetic state does, because the electron just responds adiabatically to the instantaneous state. So we find that the so the structure factor, which denotes the presence of magnetic order, its dependence on the temperature gets strongly renormalized due to bias, and this shows the collapse of the nail temperature with increasing bias. Also, the moment distribution becomes bimodal and finally gets quenched at large V. So to understand all of this, one can invoke some effective descriptions at different regions. So if you are at very low temperature, you can get the first order transition by writing an effective Landau functional of this form, where this A changes sign at Vc minus. So this is the coexistence region where it would show hysteresis. And if you solve this, you get such a behavior where these are actual, the circles are actual numerics data, and it matches quite well with this effective form. You can also motivate reduction of nail temperature if you invoke Heisenberg dynamics, but sample the magnitude of the moments from this P of M distribution. So this leads to a similar S of Q as you obtain from the exact numerics. And so it motivates the reduction of the nail temperature. And you can also do some tight binding plus disorder calculation to motivate the behavior of current with temperature at large V in the metallic phase. So to conclude, we have a formalism to access non-equilibrium steady states, where interaction and bias are treated non-perturbatively, and it's a finite temperature scheme which relies on separation of intrinsic timescales. This is geared to access dynamical correlations like collective modes, current noise, but I cannot go into them now. For the Mott insulator, we have discovered a bias-driven first-order transition akin to experiments and the emergence of a new scale, T insulator metal transition. And we find that the real space formulation is crucial for the voltage-driven system. So the paper is going to appear on arXiv tomorrow. Thank you.
Okay, so let us thank Arijit for this nice talk. Maybe we can take one question, quick question from the audience. Okay, so if not, then let us thank Arijit once again, and then we move on to the next talk. Thank you, Arijit.
Thank you.
So the next talk is by Dr. Souvik Bandyopadhyay from IIT Kanpur. Souvik, if you are online, maybe you can share your screen. Yes, it is visible now. So Souvik is going to talk about dissipative preparation of many-body Floquet-Chon insulators.
And am I audible?
Yes, you are audible.
Okay, so this talk will be basically on the preparation of many-body Floquet-Chon insulators, and the work was done in collaboration with Professor Amit Datta from IIT Kanpur, and I also acknowledge Dr. Utso Bhattacharya, Saurabh Bhattacharya ji, Dr. S. Mardanya, and the funding agencies, CSIR, the Prime Minister's Fellowship, and the Spark Project, MHRD. And I would also like to thank the organizers for giving me this opportunity to speak. So let's start off with the problem at hand. So as we know, and also as Professor Amit Datta spoke 3 days back, that two charged inequivalent phases cannot be connected unitarily and smoothly or adiabatically in the thermodynamic limit. So this is by the very definition of topologically distinct phases, so that they can't be connected without closing the bulk gap. So now the question is, can such phases be connected if the system is coupled to an external bath? So, but before we start answering these questions, there are a couple of questions which come to our mind, even if we speak topology for a mixed state. So the questions are, can a pure topological state be smoothly deformed to a finite temperature thermal Gibbs state, so while still preserving topology? And second is, how relevant is then the topology at non-zero temperature? So what is the meaning of temperature, or what is the meaning of topology at non-zero temperatures? Does the zero temperature bulk boundary correspondence still hold good at non-zero temperatures? So we'll see. And the best way to approach these questions is, I think, is to extend the definition of topological states by characterizing them through many-body operators. So how? So I will speak about a recent work in 2018 by Sebastian Dale and Bardeen. Let's consider a quadratic Hamiltonian, quadratic fermionic operators, and we'll quantify the electric polarization of any state of the system described by this Hamiltonian. So, in finite geometry, this polarization operator is directly proportional to the spatial or the position operator, the many-body position operator. But in periodic boundary conditions, it needs to be compactified to. Yes, hello?
Yes.
Yeah, okay. So this operator needs to be compactified. So it needs to be compactified in terms of the momentum translation operator itself. And in the thermodynamic limit, it is known that this expectation, which is nothing but the cumulant generating function of x, in the thermodynamic limit, it will go smoothly to the polarization operator, as we know. So now all these expectations are over pure states, pure many-body states. Now for finite temperature, let's do a simple extension and take this expectation over a Gibbs state, just like this, and see what we get. Now for one-dimensional systems, remarkably, so this density matrix can also be characterized by this matrix G, which is made up of single particle correlations in the thermal state. So this matrix G in translationally invariant system and also the density matrix rho will have certain eigenstates and corresponding eigenvalues, which we assume firstly to be non-degenerate. We'll relax this condition later and see what happens, but firstly we assume them to be non-degenerate. So now what we see remarkably is that this expectation of the polarization operator in such a thermal state, it breaks up into all the contributing terms which originate from the different bands of this matrix G, or the density matrix G. And the contribution from each band is of this form, where this part or this product contains the connection, the U1 Berry connection over each band, and this exponential is just a weight with which each band contributes to this polarization. Now there's a very interesting fact about this weight. In the thermodynamic limit, this summation on the exponent will have extensively many quantities. And as the system size tends to infinity, this weight will basically project out the lowest band of the matrix G, or the lowest band of the density matrix. And in the thermodynamic limit, therefore, this polarization operator, its expectation, will reduce to the ground state, or will reduce to only a single state like this, which is nothing but a Berry curvature kind of thing. So therefore, we find that in 1D, this expectation becomes integer quantized, like a topological invariant in the thermodynamic limit. Now there's a problem. So this projection into one single state arises only in the non-degenerate limit. So when the eigenstate on the when these eigenvalues are non-degenerate, when these are not, when they are degenerate, so two equivalent states or two degenerate states will receive equivalent weights through this exponentiation, and then this will not work. So what one finds is that, so if we characterize the topology through the expectation of this operator, at the point when the density matrix is degenerate, or when this matrix G is degenerate, the topology is undefined. So that serves as the topological critical point in this formalism. And as long as it is degenerate, the topology is defined. So increasing the temperature is indeed a smooth deformation we find, which preserves topology of a pure state, as long as the purity spectrum is gapped, or this spectrum is non-degenerate, and the temperature is finite. So now let's extend this to a 2D case, in case of Chern insulators. Now, surprisingly, for Chern insulators, this quantity, okay, now this polarization should be a vector because it's a 2D system. And this simple expectation is no longer topologically quantized. It actually assumes a non-quantized value because it's an average over Berry curvatures. But nevertheless, this quantity contains information of the topology of the state. So that is through that is through the fact that this quantity is no longer uniquely defined for a Chern non-trivial state. This was first proved by Coe and Vandermilt in 2009, and they show that this non-uniqueness of this expectation generally leads to the transverse Hall crack. But anyway, let's proceed to define a quantity from this expectation, which will serve as a good topological invariant. In the thermodynamic limit, we do one thing. We take this polarization operator in one specific lattice direction, say the direction 1, and then take its derivative about a different compact reciprocal direction, say K2. So K2 is the quasi-momentum in the opposite direction, or or in the orthogonal direction. If we do that, this function beta of K2 will also be periodic, because K2 is forms a closed S1 circle in the Brillouin zone due to the translational invariance of the system. And what we find is, in the topologically non-trivial state, when this expectation is taken over a topological non-trivial state, doesn't matter whether it's a zero temperature state or a thermal state, this function B2 shows jump singularities, or it is non-analytic, as K2 varies from 0 to 2 pi, or to the complete Brillouin zone. But in the trivial phase, this is perfectly analytic. So the derivative of the expectation of P1, which is a many-body operator, about a compact parameter is non-analytic in the topological phase, but it's analytic in the trivial. So to sum up, we see that this polarization operator basically characterizes topological states in 1D and in 1D symmetry protected insulators, and also in 2D Chern insulators. So to pictorially simplify, so in zero temperature pure states, so if one has to move from the trivial to the topological state, one has to cross a gapless critical point for some critical parameter lambda. But at a finite temperature, we see that one has to cross the point where the density matrix will be degenerate. So that is known as a purity gap closing point. So this critical point, the spectral gap closing point, is elevated to be a purity gap closing point for a finite temperature topological transition. We will illustrate all this through a very simple model, which was previously also talked about today by Professor Pinaki Choudhury. And so I will not go into the details of this model. So we'll consider a Halden model. So this is the Bayer-Halden Hamiltonian, which is periodically driven, a translationally invariant one. We couple it to an external bath, which is a fermionic bath, and whose energy densities are in a thermal distribution, a Fermi-Dirac distribution. And the coupling to the bath, system bath coupling, is bilinear in fermionic operators. The Hamiltonian, or the Bayer Hamiltonian, is also periodically driven, and it is driven through a circular potential of this form. So, and specifically, the amplitude of this drive is such that at t equals to 0, initially the system is in a trivial state. So this is the topological phase transition phase diagram of the Bayer-Halden model. So initially we are here, somewhere here, so that the system is topologically trivial. But the Floquet Hamiltonian, which is the effective Hamiltonian for Strauss, so the Floquet Hamiltonian will be topologically non-trivial. So V0, the amplitude is chosen in such a way. So now the question is, since there is a connect also to a connection to a bath, what happens in the steady state? Does the system reach a steady state?
So 2 more minutes. So 2 more minutes to go.
Okay. Yeah. Okay. Thanks. So the system bath interaction specifically is of the form. So this is the triangular Bravais lattice of the Halden model or graphene. And the bath is of the form such that it connects to every Bravais lattice point independently. And the bath is also chosen to be in a thermal equilibrium, and its energy distribution follows a Fermi-Dirac distribution at a temperature T or inverse temperature beta. Also, on top of that, we assume that the system bath coupling is weak enough such that only self-energy corrections due to the bath are relevant at asymptotic times, so that there are no direct scatterings. And also a high frequency driving, so that the different Floquet sectors of the Floquet Hamiltonian are also decoupled from each other. In this limit, let's observe at stroboscopic instants of time after very long times. So I will not go into the details of this line because I seem to be running out of time. So what I will stress is, if we do all these approximations, it can be shown that in the stroboscopic steady state, the system reaches a stroboscopic steady state after a long time. And the occupation of the Floquet bands in the stroboscopic steady states contains contribution from each photon sector. But surprisingly, if one can make the system bath coupling constants selective in energy, such that only one energy is occupied, it is possible to dominantly occupy only a single sector at a sufficiently high frequency. So this is also discussed in these two references. So anyway, nevertheless, under all these conditions, which are a bit stringent, but still, we get a steady state stroboscopic density matrix, which is nothing but a Gibbs state at a temperature beta, which is the temperature of the bath, of the Floquet Hamiltonian itself, which is topologically non-trivial. So we repeat our complete formalism of this polarization matrix on this stroboscopic topological state. And we see that, as we have predicted before, the contribution from the ground state band of the Floquet Hamiltonian approaches 1 as system size increases. So the formalism basically reduces to that of a pure state of the ground state Floquet state. And also the function beta, which we defined as the derivative of the polarization operator, it shows a non-analytic jump singularity at some point, establishing the topological non-triviality of the state. So what happens to the corresponding spectrum and the current? So this is basically the initial spectrum, which is topologically trivial. The Floquet spectrum, which is insulator in the bulk but has gapless edge states. And this is basically a single particle current in a cylindrical geometry with chiral edge modes. So as I increase temperature, what we see is that the edge modes starts depopulating and the edge current decreases. So gradually the bulk boundary correspondence disappears for finite temperature states. Nevertheless, we can define the topology through observables which can be measured. So to summarize, a finite temperature Gaussian state can be smoothly deformed to all finite temperatures as long as the purity spectrum is gapped. The macroscopic polarization operator can quantify topological phase transitions in both symmetry protected insulators and Chern topological systems. However, unlike unitary dynamics, topologically inequivalent Chern phases can indeed be connected dissipatively, even for thermodynamically large systems. Now about mixed state topology, although we see that the bulk boundary correspondence gradually disappears as temperature increases, the topology can still be detected through certain operator measurements in interferometric measurements, as suggested in this paper by Sebastian Gale and Bardeen, and a direct measurement of the many-body Chern number through the polarization operator in a recent archive by Xian and Peter Zoller. So outlook, so what did we achieve or what can we do in future? A new paradigm, an observable based study of topological states and zero and finite temperature. And also understanding topological phase transitions through the thermalization of operator expectation. This also raises the question what happens in isolated quantum systems at long times. So with this outlook, I conclude the talk. And I again thank the organizers for giving me the opportunity to speak.
Okay, so thank you, Shobik, for the nice talk. And now we have one question from Adip Agarwala. Adip,
Yes.
please go ahead.
Hi, Shobhik.
Yeah, hello.
Yeah, I wanted to ask, so if in a driven system, when you think about the Fermi distribution, are you
Yeah.
still thinking of a finite chemical potential, or you're thinking that once the system has reached a steady state,
Yeah.
I just think of the final density matrix and don't think about the like an equilibrium setting?
Yeah. So in this talk, so about so first of all, the bath was chosen to be at a finite chemical potential. But in this talk, we didn't speak about the non-equilibrium density matrix during its evolution. So the steady state seems to be at equilibrium with the bath and having the same chemical potential of the bath. So basically, the chemical potential or the filling of the Floquet states in the stroboscopic steady state at infinitely long times lies at the gap of the spectrum.
I see. Okay, thanks. So in some sense, the bath does not get heated up.
Yeah, exactly. So that is the assumption theoretically, but experimentally, of course, I don't know.
Okay, yeah, thanks.
So do you have more questions here? Okay, so if not, then let us thank Shobik once again. And this is the end of the session. Now I request the organizer to take over for any announcement or any other things.
Yeah, let's thank Tapan for chairing the session. And the next session will start at 12:05. So we can have this in between time as a discussion session where the speakers are available. If someone wants to ask question, please go ahead.
Okay.
Tapan?
Yes, thank you, Manoranjan. Yes.
Okay, thank you. Sanjay, 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 are you there? Nilotpalda.
Hello. Hi, Manoranjan.
Good morning.
Good morning. Yeah, good. I'm there already.
Yeah,
So,
I know. I mean, I've seen, noticed that you're always there.
That's great. Yeah. So what I wanted to know that we are having 30 minutes, 25 minutes presentation and 5 minutes for discussion.
Discussion, yeah.
Okay, fine.
And the
Yeah.
other one is 12 plus 3.
12 plus?
3.
12 plus 3. Okay, great.
Yeah.
So, hi Sunil.
Hi Nilotpal, how are you doing?
Great. Nice to see you.
Yeah,
so can you share your stuff here? Maybe?
Yeah, I will start.
Manoranjan, so I will start exactly at 12:05 or I will wait for a few minutes to get that gathering.
Yeah.
1 or 2 minutes here and there should be fine.
Okay.
Son is
Can
not
you
here
see
yet.
my screen?
Yeah, we can see.
Second speaker.
Yeah, you may go to the full screen mode.
Yeah.
That's cool. Yeah.
Me as well, right? So I'll stop my video because it just takes up a lot of time.
Yeah, that's okay. I mean, yeah, fine.
So I'm ready whenever you ask me to start.
Yeah. I just wait for 2 minutes. Let's see. Yeah.
So how are things in Delhi, Nilotpal?
Yeah, it is now, you know, that it is picking up again. So we are not sure whether it is a real picking up or it is a effect of, you know, that increase in testing and all. So media says like that, but we are not knowing exactly.
Here things are bad. In Pune has a huge number.
In Pune, yeah? Oh, is it? Yeah. I mean,
I had to test myself last week. Turned out negative. So far, it's okay.
Oh, really? That's great.
We had a bunch of cases in the institute.
In the institute itself, and then where you are staying, it is in the institute premises or you outside?
I stay outside, but I come to the lab daily, and so we almost have a case per day in the institute.
Oh my God.
Oh, it is terrible.
Yeah. So last week there was a scare because somebody in the engineering section became positive, and I am the faculty in charge. So he was the guy who was making all the files, and I was signing on them. So
okay, my God.
So I had to get myself tested. So far it's negative, but we'll see how far we remain.
Scary indeed, because file signing and all, it is a matter of touch anyway. So
yeah, exactly.
So Nilotpal, are the DST offices functioning?
We are functioning every day.
Okay.
Today I took leave because I know I cannot attend this meeting from my office because a lot of phone call comes and here and there. So But
Okay.
anyway, otherwise it is all functioning each and every day.
And with full strength?
No, that is not so.
Okay.
People are on and off, come and go, and then that supporting stuff is not in full strength.
Okay.
They are not allowed in full strength.
33% or something, right?
Yeah, something like that. Because I mean, I have 2 or 3, but I am only getting allowance for 1.
Right.
Something like that.
So, Nilotpal Das, shall we start?
Yeah, we can start.
Welcome to the second session. Now, may I request Dr. Nilotpal Ghosh from SERB to chair the session.
Thank you, Manoranjan. Thank you for this opportunity. I'm feeling honored anyway. So today we are having in this session 3 talks, 2 of them of half an hour, and then third is for 15 minutes. The first speaker is Dr. Sunil Nair from ISSR Pune. The topic is temperature dependence of spin-Seebeck effect in a mixed valent manganite. Sunil, please take over. Sunil? Hello? Sunil, are you there? Hello?
Hi, Nilotpal, can you hear me?
I can hear you, but I cannot see your screen.
Right. There was some issue with my connection.
Yeah.
Is it okay now?
Yeah, now it's fine. It's fine.
Okay, so
Please,
I'll
please
start.
start. Yeah.
Sorry for the brief problem. So let me start by thanking the organizers for inviting me to give this talk. Today I'm going to talk about something called the spin-Seebeck effect and some of this work which we have recently done. I have presented this in its initial form in some places last year, so it is possible that a couple of the people in the audience have already listened to parts of it. So I'm Sunil Nair from ISSR Pune, and so this is the group of people who was involved in this work. This is primarily the thesis work of my PhD student, Avirup De. Arup was a postdoc with me, was involved in the initial part of the instrumentation. Professor Satish Ogle and his student, Dr. Rajesh Mandal, were people who were involved in making thin films for us, and that is the devices which we have used. This paper has been published in the January of this year in PRL. So if somebody is interested in more details, you can look that up. So this is the outline of my talk. I will start by a very brief introduction to the spin-Seebeck effect. Spin electronics is the generic term given to all such kind of magnetothermal effects, and quickly run through how this field has evolved and the possible problems and artifacts which one may encounter when one tries to measure it. And then I will move on to the work which we did on spin-Seebeck measurements on lanthanum, calcium, manganese, platinum bilayers, and the key results which we obtained therein. And there are a few of them. We see for the first match, a perfect match with, for the first time, a perfect match with theory in the low temperature regime. And in the vicinity of the magnetic phase transition, we see an anomalous temperature dependence. And I will briefly talk about the reasons why we think we are seeing these effects. So spin electronics pertains to the generation and manipulation of thermally driven spin currents. So what are spin currents? Of course, probably this audience does not require this introduction, but nevertheless, if you look at a normal conductor, you have current flowing through it. There is no particular spin orientation, and the current is unpolarized. So that means that you have a charge current, your effective spin current is 0. Now, if you have a spin split density of states, and you can have a finite amount of spin polarization, which means that you have more spins of one character and less of the other. And so in addition to the charge current, you will also have a finite spins current. Now, if the spin split density of states is such that the Fermi level crosses only one of the spin split bands, then you would have a fully spin polarized current, which means that in addition to a charge current, you have a very large spin current. Now, the reason why people are interested in the spin Seebeck effect and spin current electronics in general is the chance of us generating pure spin currents, which means that this is something which can be set up in a magnetic insulator. So you can actually have zero charge current. There is no free charge carriers to move around, but you have a purely magnon driven spin current. Since spin current interacts and decays at a rate which is very different from charge currents, the hope is that some of this can form the next generation of spintronic devices. Now, though the area of spin currents is not very old, the fact remains that the genesis of this can be traced to quite some time back, though they were not necessarily realized as being a spin current phenomena. For instance, if you just look at the standard Hall effect, as it was discovered in gold, you apply a magnetic field and you have a generation of a voltage which is perpendicular to the direction of the applied field and the applied potential difference. Now, if in case this, instead of gold or bronze or whatever, you take a metal which is magnetic, then you also have something called the anomalous Hall effect. The anomalous Hall effect can come from a number of possible reasons. There is the side jump mechanism, which works when you have large disorder. You have the very phase. And what is of interest more to our case is something called as Smith's asymmetric skew scattering. So what happens here is that I have a scattering site which is inherently magnetic. And when I have a charge current which flows in, depending upon the relative orientations of the spin of the incoming charge vis-a-vis the scattering potential, you can have a preferential deflection of charges onto either side. So what you have is more of one kind of charges on this side and less on the other. So which basically sets up a spin potential difference across the ends of this conductor. Now, if you replace the magnetic scattering potential just something which has a large spin orbit coupling, you have the spin Hall effect, which means that don't necessarily require a material which is magnetic, but you have a charge current and it scatters through this scattering potential which arises from a large spin orbit coupling, and you can have a deflection of either spins into the opposite ends of your specimen. Now, the spin Seebeck effect is relatively new. This effect was discovered about a little more than a decade back by the Japanese groups. And so what you have here is the basic idea is that instead of in analogy with a standard thermocouple and the standard Seebeck effect, when you have a magnetic metal and you apply a temperature gradient to it, in addition to the Seebeck effect, which is a charge current, you can also have a spin asymmetry, and then you can have a spin current flowing through your system. Now, the spin current cannot be directly read off, and so the best way to do it is to actually convert your spin current to a charge current and then measure that one. So how does one do it? One typically does it using what is known as the inverse spin Hall effect. So I briefly talked about the spin Hall effect in the previous slide. So there what I have is a charge current which flows, and then it generates an effective spin current. So you can have the inverse of it, which means that you can have a spin current which is flowing, and that can, by the inverse phenomena, generate a charge current. And charge currents is what we are more familiar with in dealing with in laboratories, and it can be easily measured off. So how does one achieve this in real life? One basically use a high Z element, like platinum or tungsten or tantalum. So use a heavy metal and you deposit it on the material which you want to investigate. And any spin current which is pumped through this paramagnetic metal then just converts itself to a charge current, and you can directly read that off as a potential difference across this effective resistor. And the voltage which is generated is given by this formalism, and the magnitude of this voltage directly depends upon the spin Hall angle of this system, which is a intrinsic material property. So systems like platinum, tungsten, and tantalum have reasonably large spin Hall angles, and so they are the ones which are commonly used. On the other hand, gold has a smaller spin Hall angle, so you can use gold, but the signals will be smaller. Copper has an extremely small spin Hall angle, so if you typically use a copper electrode on top, you won't pick up any spin Seebeck signal. The other interesting thing here is that there are some systems which have a spin Hall angle with the opposite signs. For instance, if you move from platinum to tungsten, you will flip the sign of the spin Hall angle, which means that now your charge to spin to charge conversion will also flip its sign. So that is something which we use in the lab to convince ourselves that what we are actually measuring is an intrinsic property and not arising due to spurious effects and so on. Now, the first observation of the Seebeck effect was, as I said, by the Japanese group in Sendai. And what they did was to just take a sapphire substrate and deposit permalloy, which is a soft ferromagnet, on it. They applied magnetic field in plane. They also gave a temperature gradient in plane, deposited 2 platinum bars on top of it. And from this, they could pick up a voltage, which was, in their eyes, a manifestation of the fact that you have a spin current flowing through these ends, and when it crosses this interface from this magnetic metal to the paramagnetic heavy element, you have a spin to charge conversion, and that is what is read off in this fashion. On either ends, you will see a flipping of the sign. If you don't have this platinum bar in place, you would then see no voltage, which was taken to be a signature of the fact that in the absence of a spin to charge conversion layer, there is no voltage to be measured. That is something which they used to claim that this is an intrinsic effect. However, a permalloy is a magnetic metal, so there are a large number of possible spurious artifacts which can arise. And so the acid test of the existence of the spin-Seebeck phenomena was a follow-up paper by the same group a couple of years later, in which they demonstrated the same effect on a garnet. So the system which they used was a lanthanum yttrium iron oxide system. Now the garnets are extremely popular in this area because they are really good insulators. They have a band gap in excess of 3 eV, and so there are simply no charge carriers to be had around to interfere with your measurement. And there again, they using a slightly different geometry showed that one could pick up a spin to charge conversion, almost analogous to what they had seen earlier in permalloy. And this was then taken to be proof of the fact that here you actually have a genuine spin current, and what you are seeing in your charge current measurement is a manifestation of the spin current being converted to a charge current. And ever since that report, the garnets, especially yttrium iron garnet, has emerged as really come out as a model system, and a vast majority of work in this area has used these kind of systems for their investigations. Now, though the initial, so there are 2 kinds of measurement geometries which are commonly used. One is the initial one, which is known as a transverse configuration. The names are a little misleading. One doesn't need to pay too much attention to it. But very soon it was realized that this measurement geometry has problems, and what one is seeing is probably not a true spin current, and there are a large number of artifacts which can interfere with this measurement. And now the community has kind of narrowed down to what is known as a longitudinal measurement. So the geometry is like this. So you have here the magnetic material which is of interest. You magnetize it in plane. Perpendicular to it, you apply a temperature gradient. You have a platinum bar on top of it, and you can pick up a charge current which arises due to the conferent in this fashion. So the longitudinal measurement does give you reproducible measurements, and it is the measurement geometry of choice at this point, but there is a problem. And the problem is that by virtue of this geometry, there is no way in which you can avoid signals which arise due to the anisotropic Nernst effect. So the anisotropic Nernst effect is it's not anisotropic, sorry, anomalous Nernst effect, ANE. So the anomalous Nernst effect is simply a thermal equivalent of the anomalous Hall effect in some senses, and you simply can't get away from it in this measurement geometry. So I have a temperature gradient in this direction and a magnetic field applied in this direction. I will always have an anomalous Nernst effect from my magnetic subunit if my magnetic subunit has charge carriers in it. So that means if it is an insulator, I don't need to worry about it. But if in case it is a metal or a dirty metal, there is no way in which I can get around this problem. So that means that if I have to make an estimate of the true spin current, I would necessarily need to subtract out this anomalous Nernst effect. In the early days, there was also some doubts raised about the fact whether there could be a proximity-induced anomalous Nernst effect in the platinum itself. The reason being that platinum is on the verge of a Stoner's instability, and there were some suspicions that when you place it in close proximity to a magnetic system, you can actually have an anisotropic anomalous Nernst effect coming in the platinum bar itself, though that has now been effectively ruled out. So the moral here is that the longitudinal mode is preferred, but one has to always worry about cleanly disentangling the anomalous Nernst effect from the true spin-Seebeck signal. So a few years back, we decided to make a setup to measure this, and this is how it looks like. It looks, it's basically just a closed cycle refrigerator mated with a locally bought electromagnet. Over the period of time, we spent a fair bit of time in reducing its noise level and so on and so forth. So this is wholly enclosed in a Faraday cage and so on. And now we have a setup which we think is as good as any in the world. We have a noise floor of the order of 5 nanovolts or so. So extremely small signals can be reliably measured off. Our higher field, our field ranges are limited because it's a small electromagnet. We can't go to anything more than 2.5 kilohasted, and the devices are made out of pulse laser deposition or even single crystals and sputtering and so on. So these were the initial test measurements. So this is your magnetic system. On top of that, you have a platinum pad. You measure off the voltage, and this was on YIG just to make sure that we are not doing anything stupid. And this is the spin-Seebeck signal as a function of the applied temperature gradient. This is how the hysteresis would look like. And if you change the...
Hello.
হ্যাঁ আমি বলছি কি ওই রকম করে মানে একটা পিডিএফ পাঠিয়ে দিবি মানে আমার সার্টিফিকেট অন্যজনও পড়বে তাই তো
Please switch off the microphone.
Nilupal, you can probably do it from your side. Okay. Okay, so this is how the profile would look like if I change the angle between the applied magnetic field and the temperature gradient. Now, when we started, when we had a system in place and we were looking at possible systems to investigate, we decided on the mixed valent magnet for a particular reason, because by that time there had been a couple of reports which had already come in on lanthanum strontium magnetite, and the conclusions drawn therein were completely in contradiction to each other. The first one said that they could not see a spin-Seebeck signal at all, and all that they were measuring was basically the anomalous Nernst effect. And the second one said that they could not see an anomalous Nernst signal at all, and all they were measuring was the spin-Seebeck effect. So we thought that this might not be a bad place to enter, and we decided to go not with LSMO but with LCMO, primarily because of the fact that the optimally doped LSMO has a transition temperature which is higher than room temperature, and that would not have been very convenient for us. So we looked at the optimally doped LCMO, assuming that the physics would be more or less similar. And this is what we do. So basically we use LAO, and later we even tried STU as a substrate. We deposit a thin film of LCMO varying from 200 to 400 nanometers. And using sputtering, we deposit platinum, tungsten, tantalum or something on top. So without the heavy metal overlayer, we first measure off the anomalous Nernst effect, because lanthanum calcium manganate is a magnetic metal. Though it is a dirty metal, it's still a metal. So you can't really get away from the ANE signal. And then we coat a layer of this heavy element, and typically of the order of 5 to 15 nanometer thick. And then we measure what is basically a combination of the SSC and the ANE, and then we have to subtract out one from the other to get the true spin-Seebeck signal. So this is how this looks. So for instance, what I'm showing here is the total signal here in brown, and this one in blue is the ANE signal. And so when I subtract the two, I actually get the true spin-Seebeck signal. Now, as I had mentioned earlier, the sign of the inverse spin Hall effect goes directly with theta SH, which is the spin Hall angle of that material. And so if I change platinum by a metal which has an opposite spin Hall sign, then my voltage should flip. And so tungsten does that for you. So we replace platinum by tungsten, and what you now see is an exactly reverse direction of the spin-Seebeck signal, which is also shown here. And so this convinces us that what you're measuring is actually the true spin-Seebeck signal with the anomalous Nernst effect cleanly subtracted out. And this is probably the reason why the earlier reports were in such a mess, because this is one from the paper in which they had claimed that they could not see a spin Seebeck signal, or they see a feeble one. So here, if you look at it, you have platinum, which is in red, and tungsten here, and you can see that both of them have the same sign. So there is no reason, there is no way in which this can happen if they have cleanly disentangled the ANE signal from the SSC signal. So with this telling us that a measurement is reasonably reliable, we now look at the temperature dependencies of the ANE and the LSSC separately. And on the top panel here, I have the magnetization and the resistivity plots. As is known in manganites, resistivity being a population phenomena, the transition can lie slightly higher in temperature. And ANE, by virtue of being a magnetotransport measurement, actually starts exactly at the point at which it becomes a metal. On the other hand, the spin Seebeck signal arises from a magnon propagation through a system. So that kicks in a little lower in temperature when the system is actually more magnetic. And this is again something which convinces us that we have cleanly disentangled these signals. So if you look carefully at the spin Seebeck signal, what you see is that you see a hump-like feature deep into in the magnetic regime. This is a characteristic of all spin Seebeck measurements, which are temperature dependent. And this peak or hump-like feature arises because of the fact that what you see here is an interplay between two competing phenomena. As you decrease the temperature, your magnon population decreases, but as at the same time, the magnon propagation length or the lifetime increases. And it is a competition between these two which gives rise to this kind of a hump here. And this is seen in almost all temperature-dependent LSSC measurements, irrespective of the system you're looking at. Now, there have been a couple of theoretical predictions about how the magnon spin current should vary as a function of temperature, especially at low temperature, where other factors like magnon phonon scattering and so on is less. So this is known as a magnon spin current theory, and the equations are here. It depends upon a bunch of things. It depends upon theta sh. It depends upon the population of the spin polarization into a non-magnetic layer. It depends upon what is known as a spin mixing conductance, which is basically telling you how transparent your interface is to the pumping of spins of a spin current and so on. But if you leave the moral here is that all the predictions claim that the voltage which you measure, the spin Seebeck voltage, should go as T raised to 0.5 in the low temperature region. And interestingly, this had never been observed earlier. And the closest people had come to was in YIG, which I said is a model system for these kind of measurements, where they had seen an exponent value closer to 1 and so on. So when we look at our system, you can actually see in the low temperature region a very good fit to the spin current model. So what you have here are two graphs with different thicknesses of platinum on top. And you see that they always hover around this 0.5 mark. And so this is actually the first time there has been an experimental verification for the spin current theory in this form, that you have to just to go to show that somehow the LCMO system was very good for this. Now, there is one aspect which has been missed in literature, and that is the fact that people, when we do a spin Seebeck measurement, you apply a temperature gradient across this device, and you measure the spin Seebeck effect as a function of or as a function of magnetic fields or of temperatures and so on, and you normalize your signals by the temperature gradient, and that is how it is analyzed. However, the fact remains that in your device, there is a big part from your substrate. Your thin film, which is magnetic, is actually just a few nanometers thick. So the thermal conductivity of the substrate is something which should have been taken into account, but was never done. So what we did was to replace the lanthanum aluminate substrate by a strontium titanate one. Both of them have very different thermal conductivities. And when we tried to estimate, using a simple resistor kind of a network, as to what would be the effective temperature gradient across my magnetic subunit, and that is plotted here. And very soon we realized that the upper bound of fitting, or the point till which we actually see a good match with theory, is determined by the fact that whether your effective temperature gradient across the LCMO film is constant or not. So at the point in which you see a dramatic change in the effective temperature gradient across your LCMO is when your fitting starts to deviate. So this tells you that when one is trying to look at the spin-Seebeck signals in these kind of devices, and it is important not just to look at the effective delta T across the device, but to actually go back and calculate what the effective delta T is across your magnetic subunit, because that is where all the auction is coming from. So
We are having 5 minutes more.
yeah, I will finish in 5 minutes.
Yeah, sure.
So, so why is it that the standard system, which is yttrium iron garnet, never showed a good match with theory? So I had shown you a large equation earlier, which was giving you all the individual contributions which goes into the effective voltage, which you measure out as a spin-Seebeck voltage. And we tried and see to look at what are the temperature dependencies of each of these units itself. Luckily for us, most of this has been measured in the past. So if you look at the spin Hall angle, it is temperature dependent across our measurement range. So that should not be a contributory factor. You look at the extent of spin polarization, which is pumped into the non-magnetic metal, it has a slight temperature dependence at low temperatures. Now, if you look at this, which is basically the spin mixing conductance, which is indirectly estimated from FMR measurements using the line width, so this is how it looks for in a system like YIG. It is very strongly temperature dependent at low temperatures. For LCMO, there have been no recent reports, unfortunately, but we could manage to get one old report of exactly the same composition, and this this black filled curves is one which you're looking at. So below 100 Kelvin, there is no report of a temperature dependence. So this is probably the reason why we could actually manage to get a good match with theory in this case. The fact that the spin mixing conductance remains invariant, whereas that was not the case in YIG. So now we go to the temperature dependence of a spin-Seebeck effect closer to the magnetic transition. So here again, there have been a couple of contradictory reports. The earlier ones on YIG showed that the spin-Seebeck effect showed an exponent of 3, whereas the magnetization showed an exponent of 0.5, which is what you would expect from a mean field system. There's another report which showed a spin-Seebeck exponent of 1.5, which is still a factor of 3 larger than the magnetization one. So the consensus was that for some reason in YIG, the spin-Seebeck exponent was always larger than that of the magnetization. Now, however, theory was always insistent that that should not be the case, and that the spin-Seebeck effect should follow the magnetization. That means it should effectively have the same exponents. So we try to repeat these measurements in the, do careful measurements in the vicinity of the magnetic transition, and we actually see a feature which is similar to what had been reported earlier. This is the temperature dependence of magnetization. We have an exponent of 0.35. On the other hand, if you look at the temperature dependence of the spin-Seebeck effect, we have values varying 0.64 to 1.25, depending upon the thickness of the platinum which you deposit. And herein lies the clue. So some of this I've shown you earlier. So theta SH, of course, does not vary in this magnetic transition region. The lambda NM also does not vary in this region. The spin mixing conductance has a strong temperature dependence. Unfortunately, this data is not good enough from the earlier report to actually see whether it has an exponent which matches well with magnetization or not. That is something which we plan to do later. So our speculation at this is that the mismatch between theory and experiments in the vicinity of the phase transition region principally arises because of the fact that the spin mixing conductance is not varying in consonance with the magnetization. And the thickness dependence, which we see as a function of different platinum thickness, is an indicator to this end. So I hope I'm in time and I would summarize. So what we have done is to cleanly disentangle the anomalous Nernst effect from the spin-Seebeck effect in an LCMO platinum, LCMO tungsten bilayer. At the low temperature region, we see an extremely good fit with theory. It was the first of its kind. Near the transition temperature, we see and reconfirm what some others have seen in the past, that the longitudinal spin-Seebeck effect does not follow the magnetization. We can state with firmly that the temperature dependence of each contributory factor has to be ascertained before one tries a match with theory. This is something which had been missed out on earlier. And we also show that the role of the spin mixing conductance is probably what is the key to understanding the temperature dependence of the spin-Seebeck effect. So right now I'm in the process of of trying to build an FMR setup, which will then complement these measurements so that we can also independently measure the temperature dependence of the spin mixing conductance in these kind of systems. So with that, I will stop, and thank you very much for your attention.
Thank you, Sunil. It is a very interesting talk, and the floor is open for questions. So the audience, if there is any question, please. Hello.
Yeah.
Yeah, it is again gone. So if there is any question, I'm
Hello,
not finding any chat box, any question.
Sunil.
Shubhankar.
Yes.
Tell me.
Very nice talk. Just one question about manganites. Let's say if we take LSMO instead of LCMO, do you expect the similar behavior or something different?
I actually think that the behavior will be rather similar. Though, as I told you, the only reason why we picked up LCMO was because with our equipment we can go through the phase transition in a cleaner fashion. With LSMO, I would like to do instrumentation again to go to higher temperatures. So I don't really expect a great deal of physics to change moving from LSMO to LCMO, to be honest, at least for the optimally doped compounds, which is what it is.
Yeah, thank you. Thank you also for making my talk simpler, because today afternoon I'm talking the similar.
Yes, I look forward to it.
Good, thanks.
Okay. Thank you very much. Thank you very much, Sunil. So, yeah, so we are going for the next talk. Just to make an announcement that this session, all the talks are for 30 minutes. So this is over, and now we will be waiting for the next talk from University of Cambridge, Dr. Sian E. Darton. Is she there?
Yes, I'm here. I'll just share my screen.
Great.
Okay.
Hello.
Hello. All right. Well, thank you very much.
Yeah. Thank you very much for sharing your screen. That's fine. So we are having 30 minutes. So are you ready, Dr. Darton, to start over? Yeah.
Yes, I am. My cat is just sat on my webcam.
Yeah, fantastic. So
when
now there's a talk by Dr. Sian Darton from University of Cambridge. The title is Magnetism and Magnetocaloric Effect in Low Dimensional Lanthanide Borates. So Dr. Darton, you may start. Yeah, it is 30 minutes, 25 minutes for talk and 5 minutes for discussion.
Okay, all right. Well, thank you very much for the introduction, and thank you very much for inviting me here to speak today. My name is Sian Darton. I'm from the University of Cambridge, and I'm going to talk today about some of our work on lanthanide borates, both looking at the magnetism and the magnetocaloric properties. Before I begin, I'd really just like to acknowledge the people who did the work, in particular Nicola Kelly, who's a current PhD student Paramita Mukherjee, who did some of this work during her PhD. We received funding for this from the UKRI, so UK funding agency, and also from the Winton Programme for the Physics of Sustainability. So in my research group, we're interested not just in magnets, but in thinking more widely about structure-property relationships in complex oxides. So in addition to our work on magnetism, we also look at new electrode materials for rechargeable batteries, and a little bit on structure-property relationships in hybrid photovoltaics. But today I'm going to talk mainly about magnetocalorics, but that this does also link into some of our work on novel order in frustrated magnets, because we are looking at frustrated magnets as magnetocalorics. So over the last few days, we've heard a lot about novel properties, and a lot of those exist at low temperatures. And when we do these measurements, we need to cool, and typically we would use some kind of cryogenic gas, typically nitrogen if we want to get to 80 Kelvin, or helium if we want to go lower. And as well as use in scientific experiments for cryostats, these cryogenic gases are also used for cooling the superconducting magnets in applications such as MRI scanners, and also as quantum computing comes online, there may be the need to have enhanced cooling. So helium is actually a finite resource, and it's a byproduct of natural gas extraction. And over the last 10 to 15 years, there have increasingly been shortages due to difficulties in the supply, and there being fewer reserves. And certainly in the UK, when there are these shortages, typically if you're not a hospital using it for a medical application, a clinical application, then it's very difficult to buy it. And this has been sort of widely publicized in, sorry, it's not been widely publicized. Says the BBC in various sources in the US, asking whether, like, highlighting this helium shortage and asking questions about the use of helium in party balloons. So it turns out the helium in party balloons is very contaminated, so please don't use them in your cryostats. But it does highlight a real issue with helium. But it turns out that actually there are alternative ways to get to these cryogenic temperatures. And these are known technologies which have been used in space applications for a long time. So should be changing slide, I apologize. In satellites where you can't go up every week to 10 days to change your dewar, the detectors, which require cooling to below 2 Kelvin, are cooled using solid state cooling, using dilute magnetic salts, and driving cooling by application of a magnetic field to drive a change in entropy, which can then allow for cooling. And the way this works is using the magnetocaloric effect. So we can think about a material at some particular temperature and in some magnetic field, and it will have an entropy A. And if we then change the magnetic field to apply a field to polarize the spins, if we're in a paramagnetic state, then what we do is we generate a state which is more ordered. So we go from A to B. And then if we remove our field, but we do it in such a way that we do it adiabatically, such that the entropy doesn't change, we can then go from B to C. And in doing this, we change our temperature by some difference, delta T. And so this you can do very effectively, particularly in materials which have large magnetic moments and close to the magnetic ordering temperatures, where the difference on application of a field is large. And so this is what's employed in these satellites, where dilute magnetic salts, which have very low ordering temperatures because the magnetic ions are very well separated, are used to cool to low temperatures. So we came into this thinking about, are there alternatives to dilute magnetic salts? And thinking about, well, how would we do this if we want to get to a low temperature, have a low ordering temperature, so we can use this effect to cool to the temperatures we want. And the strategy we've approached is thinking about this by using geometrically frustrated magnets. So these are magnetic systems where there's a delicate competition between competing magnetic interactions, such that the magnetic ordering is suppressed to much lower than the temperature you would expect by simply looking at the device temperature, so the strength of the interactions. And typically you can host this type of frustration in sort of geometries of triangles, where if you imagine an antiferromagnetic lattice, you have a spin up on one corner, a spin down on the other, and then on the third corner, there is from one spin it wants to point up, and the other spin it wants to point down, and so you suppress the ordering temperature. And so this is where we started looking into this, and we decided to combine these frustrated magnetic lattices, where we're suppressing the magnetic ordering temperature by typically a factor of 10 from what we might expect in an equivalent non-frustrated system, with materials containing rare earth ions. So rare earth ions are attractive because they have very weak interactions between the orbitals, which means that you have very low ordering temperature. And then again, if we have frustration, we're suppressing the ordering further. In some rare earths, we can generate very large magnetic moments, which means we can have a very large theoretical change in the magnetic entropy. And often the rare earth ions are chemically very similar. So this means we can go away and we can make a whole bunch of different materials because the chemistry of the environments they sit in is very similar. But so that contrasts with the very different magnetic properties, which are very sensitive to the crystal electric field. And so this gives us a bench, sort of a playground, a platform to look at lots of different materials, different similar materials, to try and understand how we might optimize things. And the final thing is that particularly if we're looking at oxides or borates, as I'm going to talk about today, these are relatively stable chemical material, chemically stable. So they're not going to react with moisture or air. And so you don't have to worry so much about how you encapsulate them. And with the dilute magnetic salts, which have traditionally been used, these contain crystalline water. And so if you have them sat on a table, the content of the water changes in the crystal, and this will change the magnetic properties. And so you have to be very careful about encapsulating it such that the material doesn't change. And this is less of an issue for the materials I'm going to talk about today. So this sort of idea has been looked at before, and sort of the sort of material which most of these sort of more dense magnetocalorics compared to is gadolinium, gallium, garnet. We heard a little bit about garnets earlier today in the previous talk. I'm not going to spend a lot of time talking about this. The garnet structure is shown here with the rare earth gadolinium ions shown here in white. And the magnetic lattice is comprised of corner-sharing triangles, which form these 10 members rings, which are bifurcated, and they're interpenetrating. So this is a highly frustrated system, and it has a very complex magnetic phase diagram, which is still the subject of some debate. I've shown here some early work from Peter Schiffer and his co-workers that have one sort of phase diagram showing paramagnetism down to very low temperatures. But what's important of the magnetocaloric effect is that this has 7 unpaired f electrons, so it's got a large spin of 7/2, and it has Heisenberg's isotropy. And if we think about this in terms of the entropy we could release, the maximum per gadolinium is going to be 17.2 kilojoules per mole. So when we first started working on this, we didn't come straight to the garnets. We actually started thinking to the borates. We started thinking about other garnets. And you can go away and you can make these rare earth gallium garnets for a whole bunch of different lanthanides. And we can do this and we can calculate the magnetocaloric effect from isothermal magnetization, which is what we've done here. And you can see straight away that the change in magnetic entropy is largest for gadolinium when you go to high fields. So this is really why it's been focused on. But when you compare this to other rare earths, which rather than having the Heisenberg spins of gadolinium, have single ion anisotropy, so terbium, dysprosium, and holmium, what you see is at low fields, actually, these are slightly better. And if we start thinking about using these systems using a permanent magnet rather than using a superconducting magnet, then actually the change in magnetic entropy from dysprosium is higher, dysprosium and terbium is higher than that for gadolinium. So in lots of our later work, we've been focusing on some of these other rare earths as well as gadolinium, because if we're thinking about using permanent magnets rather than a superconducting magnet, then we want to be in this sort of low field, less than 2 Tesla regime. So we've done quite a lot of work on the garnets, and I'm not going to spend a lot of time talking about this today, but we can, by changing the gallium, which sits on 2 distinct crystallographic sites in the magnetic lattice, with other ions, both trivalent, so scandium, aluminium, indium, or changing the oxidation states of the 2 sites, we can make minor changes to the magnetocaloric effect. In the case of holmium, where the crystal electric fields are perhaps more sensitive, we can make more significant changes. But what we found, where we found we had the most impact, was actually replacing the D0 gallium, or the other ions shown here, which are all non-magnetic, is replacing those by a small amount of a transition metal with unpaired electrons into the magnetic lattice. So in the case of gadolinium, this doesn't have a large effect. But in the case of the icing spins, what we find is that at low temperatures, particularly with chromium, we get a very large enhancement of the magnetocaloric effect. And I'm not going to discuss this today, but it turns out this is related to the fact that there is some coupling between the rare earth and the transition metal lattice, which sort of drives sort of the ordering to a higher temperature. And if you're interested in that, sort of the chromium one is discussed in this advanced functional materials paper, and the manganese in this PRB paper. So having looked at these garnets, so then we asked, are there any other alternatives? I mean, garnets are very good. They are much better than the dilute magnetic salts. And as I've very briefly shown you, they have a large amount of chemical flexibility, which allows us to tune the magnetocaloric properties. But if we're thinking about the metrics for the magnetocaloric effect, if we think about this per unit mass or even per unit volume, there's a large amount of other non-contributing atoms in our material, which might be reducing our or sort of making our metrics not so attractive. So can we look at other things? And there are lots of reports out there looking at other materials, particularly molecular organic frameworks. So this is where you have some kind of metal, either individually or in clusters, connected by organic linkers, or also sort of polyanion materials where you may have a say a phosphate group or something like that, which connects the lattice. And because these are lighter sort of building units, these tend to have very high metrics for the magnetocaloric effect. So where we decided to look was at the lanthanide borates, and this is for a number of reasons. So first of all, there is a large number of lanthanide borates out there, but very little is known about their magnetic and their magnetocaloric properties. But also as an analogy with the other, because it's in the same period of the periodic table as gallium and aluminium, so there's an analogy with the garnets. So we've looked at a fair number of these lanthanides, and I'm going to just pick out a few to talk to you today. And I've picked out the ones which have features of low dimensional ordering. So I'm going to talk to you about some materials with a two-dimensional triangular lattice, the lanthanide orthoborates, and this material we've just recently started studying, barium terbium borate, and also some materials which have signatures of one-dimensional order, which was quite surprising when we started thinking about this, because these distances, the distance between the shortest distance and the next nearest neighbor distance, are not so different. But it turns out that in some of these lattices, the nature of the magnetic interactions means you see features of one-dimensional or low-dimensional order. Okay, so I'm going to start with the orthoborate, which is where we started previously. I've got this. Okay, oh, sorry, here's just showing the magnetic lattice here with the triangle. So we started looking at these lanthanide orthoborates, and these have been extensively studied as for their optical properties, and they're discussed quite widely in terms of phosphates. And when we started looking at these materials, it turns out that whilst I've shown you this crystal structure for this here, there was actually quite extensive debate in the literature about what the crystal structure was, both in terms of the symmetry of the lattice. Is it purely, is it a perfect triangles, so a hexagonal or rhombohedral crystal structure, but also in terms of the connectivity of the borate groups, with them either forming discrete B309 units, triangles, or forming some sort of continuous network. And this is just taken from Primta's PhD thesis, where she discusses some of the different crystal structures. And part of this is because well, it's quite difficult to study these using X-ray diffraction, because really all you're seeing is the lanthanide lattice. So having said that, we studied these using X-ray diffraction. And what we find is that we make very crystalline materials. And when we look at this, what we see is that we see some peaks where there will be a single peak in both the hexagonal and the monoclinic structure. We see very sharp peaks, but in others where there would be a single peak in the hexagonal structure, but two in the monoclinic structure, we see these are much broader. And so from this, we can say quite clearly that we have a monoclinic lattice. So we don't have equilateral triangles, we have distorted scalene triangles. And just to note that we can make these for a whole bunch of rare earths, and we find that they're all monoclinic. We do actually have some neutron diffraction on this, and that there are some subtleties in the interactions between the borate groups and the lanthanides, and we're still working on fully understanding what those borate groups look like. And in terms of the magnetic lattice, we have three different types of triangles shown here in these cyan, green, and pink colors. And with it's a little bit hard to see, but the different colors of the bonds showing different bond lengths. And they're all sort of distorted by a small amount, and the level of distortion is relatively similar in all of them. So having made these, we can then go away and we can measure the magnetic properties, which is what we did. And what we find is that at sort of high temperatures, we see very little above 2 Kelvin. There is this broad feature in the holmium borate at around 6 Kelvin, which is much more clearly shown in the heat capacity. And it turns out, I'll show you some evidence of this later, but this is the formation of a singlet state because the holmium is in a low symmetry site. However, in some of the other lanthanides, we see at lower temperatures sort of sharp features that indicative three-dimensional order in the gadolinium, dysprosium, erbium, and then a very broad feature in the terbium. And because of the low temperatures of these, we haven't had the opportunity to explore the nature of the magnetic structure very clearly. But we can go away and we can measure the magnetocaloric effect. And this is just showing the magnetocaloric effect versus field for all the different rare earths. These numbers probably don't mean very much, but we can compare this to the respective garnet. So what we find, and we pick the best two, the dysprosium and the gadolinium, is that in sort of all in most temperatures and fields, the borate outperforms the equivalent garnet in terms of the magnetocaloric effect, which is nice. Okay. Okay, so having done this, we wanted to look and see, can we make other lanthanide borates with triangular lattices? So the one that we've spent the most time looking at is this barium terbium borate, and this lattice, this crystal structure, forms for larger lanthanide ions, and it has a space group and symmetry of the lanthanide sites, which are the same as for terbium indate, which is reported to be a potential quantum spin liquid, where you form a singlet on one of the terbium ions, so you end up with a honeycomb lattice at low temperatures. And just as a point, there are lots of other lanthanide alkaline earth materials which also form these triangular lattices. So it turns out that this crystal structure has been known for a while, but that depending on the size of the rare earth, you either get this layered structure, or you get this structure with what look like chains of the rare earth. So effectively, you take one of your lanthanide sublattices and you sort of shift it in the Z direction to form this other crystal structure. And for a long time, it was felt that there was a cutoff in terms of the ionic radius as to when one might form the low temperature, this hexagonal phase, versus the high temperature rhombohedral phase. And what Nicola has done is she's shown that actually by sort of tuning the synthesis conditions, she can actually extend this high temperature phase down to smaller rare earths and make this terbium polymorph of the low temperature phase. Okay, so we can make this, and just as a point of note, there are these two rare earth sites shown in the different shades of purple. Okay, so we can go away and we can measure the magnetic properties of this. And what we see is that above 2 Kelvin, there is a kink. It's not so clear in the raw data, but when we look at the differential, there is a clear feature in the susceptibility, at around 10 Kelvin. And we also see something sort of similar temperature range in our heat capacity. And we're still working on the origin of this, but I do note that it's very similar in terms of the temperature to that where the singlet state is formed in the terbium indate. So that's one possibility. Of course, it could also be some kind of short range ordering. We have then gone on and measured this in lower temperatures down to 400 millikelvin, and we can reproduce the broad feature, and we do see an upturn at low temperatures, but we attribute this to the nuclear shock heat anomaly in terbium, and this is very new data, so we're working on subtracting this, and there doesn't look to be any evidence of long range order in this material. So I sort of pitched these materials as looking at them for the.
Sorry, just a quick clarification. This is terbium compound?
Yes, this is the terbium one,
okay.
Sorry.
Yeah,
yes.
okay. Yeah, thanks.
No, I apologize. So, yes, so this is the terbium one. So all of the data are on the terbium one apart from the crystal structure. Okay, so we have also looked at the magnetocaloric effect for this. Because we have 3 bariums in the crystal structure, when you look at this per unit mass or even per unit volume, the numbers are actually very low. So this is not going to be a good magnetocaloric. But it turns out if we look at this contour plot of our magnetocaloric effect, we actually see some features which might indicate something. So the first thing is that this sort of broad feature at around 10 Kelvin is reproduced in our sort of cuts through this data. So we still need to understand that. But perhaps more surprisingly, certainly to us, is that below, so as you cool further around 4 Kelvin at 0 field, slightly higher as you increase the field, we get an inverse magnetocaloric effect. So this is saying as you apply a field, you actually decrease the entropy, which is rather uncommon. And this has been seen in a few materials and ascribed to a few different things. So crystal electric field effects in sort of rare earth intermetallics, in uniaxial paramagnets containing non-Kramers ions, or first order magnetic transitions in transition metals. So we're still looking at exploring this further, but I think that what this shows is that the magnetocaloric effect, as well as being useful, is another way of thinking about exploring the magnetic data that you collect as the features can become clearer. So this is still very much a work in progress, and we're looking to get some more measurements below 2 Kelvin to explore the magnetic structure, and also to understand the crystal electric field effects, because we're sort of sensitive to the fact that particularly in terbium, with the site symmetries we have, we could be forming singlets, which would then change the nature of the magnetic lattice. So that's all I really wanted to say for this section. I hope I've shown you that we can form these lanthanide borates with a triangle. Well, I've shown you we can form them, and that there are a host of materials with high magnetocaloric effects and potentially novel magnetic phases. And I've just briefly introduced this barium terbium borate, which has this distorted triangular lattice, but appears to have some very interesting low temperature magnetic features, which we're still looking at. Okay, so how much time do I have left? Okay, I think I've underestimated how long I was going to take, but I'll keep going until somebody tells me. So we can then think about what other types of magnetic lattice. So I've already shown you that in these barium analogs, you can make crystal structures that look like they have one-dimensional chains of rare earth. And so we've also looked at some of those. So we started with a metaborate, which have these chains, which if you put in the intrachain, the next nearest over intrachain interactions form these sort of harmonic honeycomb type structures. And it's just worth noting that the perspective is a little bit tricky here, but this is shorter than this, though they are relatively similar. So again, these forms a monoclinic crystal structure, and we can make this for a much smaller range of larger rare earth ions. But what's interesting here is that as we cool them, we see sort of features which sort of may be indicative of low dimensional ordering. So we see 2 different magnetic order features in the low temperature specific heat for the terbium medical rate, which is often seen in one-dimensional systems, but perhaps more sort of indicative of low dimensional ordering is we see these in our isothermal magnetization in the neodymium and in the terbium. We see our isothermal magnetization sort of plateauing at 1/3 the fully polarized magnetic field, which sort of is characteristic of often seen in what quasi-1D systems. So though I skipped through this in the interest of time, but there is this very broad feature in the praseodymium borate. We've looked at this using neutron diffraction. What's seen here is actually two data sets, one at 1.5, so below the ordering transition, and one at 30. Here and the difference shown in blue. So there's no difference, and we ascribe this to the fact that we're forming a singlet state in this broad transition because of the low symmetry site of the praseodymium. So we can measure the magnetocaloric effect of this again, and in the case of gadolinium borate, the gadolinium analog, this is outperforms the gadolinium garnet, but it's not as good as the best of gadolinium one out there. And the others are much poorer, so I'm not going to show them to you. So I'd just like to come back to these sort of signatures of low dimensional order, particularly these 1/3 magnetization plateaus. So in these materials, depending on the rare earth, that we see a couple of systems, the neodymium and terbium, where it looks like there may be sort of signatures of low dimensional ordering, whereas in the gadolinium borate, we see some features which would be indicative of 3-dimensional order. So then we can ask, well, why are we seeing such different properties depending on the rare earth? And to think about that, we can think a little bit about the underlying magnetic interactions. So in these rare earths, there are 3 interactions which are all of similar magnitude, so you can't, unlike in transition metals, you can't ignore them. So there's the crystal electric field effect, which is going to be dependent on the oxygen, but also the number of F electrons and whether you have an even or an odd number of electrons. And I think what's important here is if we have icing spins, so a 2-level system, rather than thinking about this in terms of the full J, we would have a J effective of a half. Then we can think about super exchange, which is going to be mediated through the ligands, and this is going to be directional, so it's going to depend, it's going through a ligand, so it's going to be different in this direction to this direction. And we can approximate this in a mean field limit using this equation here, when we're looking at the Weiss temperature and the spin. And we can also approximate a dipolar interaction, which is dependent over 1/r³ in this mean field limit. And here, this is isotropic, so it's only dependent on the distance, not to do with the environment around it. So depending on whether we assume we have an icing system or whether we have something which is has less spin isotropy, we can calculate these parameters. And what we find is that if we just think about the Heisenberg system of gadolinium, we see that the J and the dipolar interactions are very similar, and so that we would expect there to be three-dimensional magnetic interactions, and we would have a 3-dimensionally ordered system. However, depending on whether we use an Heisenberg or an icing spin to approximate our J coupling in our neodymium and terbium, we get very different values. And when we do this, what we find is that we have a much larger exchange along these bonds than between them. And so this, we hypothesize, might be why we're seeing this sort of quasi-1-dimensional magnetism. And I think
we are having about 1 minute left now.
Okay, all right, I apologize. I thought I was running over. Thank you. So I'm not going to spend a lot of time on this, but I just want to say that this is not the only example we've seen where we think that we might have signatures of quasi-1-dimensional ordering. So we've also looked at calcium lanthanum borates. The crystal structure is shown here with the shortest interactions shown here. Of ions. We spent less time. We've not been studying these for so long, so at the moment we only have measurements above 2 Kelvin. We see some broad feature in the terbium, which we've just got data looking at. But just to reiterate my point here what we find is actually both the dipolar interactions and the dipolar interactions are also telling us that there is one dipolar interaction. Because the distances are much shorter, these look like to be much better candidates for hosting one-dimensional ordering or quasi-one-dimensional ordering in these sort of systems. And I think with that, I've run out of time. Just to say again that these are quite good magnetocalorics. And I would just like to finish by really acknowledging the people who did the work. So Nicola, who's worked on the alkaline earth lanthanide borates, and Perimeter, who worked on the ortho and the metaborates. And I'm happy to answer any questions.
Thank you. Thank you, Dr. Darton, for a very elaborate and thought-provoking talk, I should say. So the floor is open for questions now. There is one question. The first one is by Subhra Bhattacharya. Is he there?
Yeah, I'm around. Hi.
Yeah, please,
So
carry on.
So the question is, what is the site symmetry of this rare earths? Is it D3D?
So I'm afraid I don't have those to hand, but the crystal structure for all of these are reported. So I could get back to you with them if you send me an email. I don't want to tell you the wrong thing. And they're going to be different for the different materials.
Because
so,
that would critically determine what is the nature of the low energy magnetic doublet.
Yes, and I mean, I think that we do need to do some more work looking at the crystal electric fields of these materials.
Right.
We've done it for the garnets, and we haven't quite got that far for the borates yet.
I see. Can I just quickly ask a following question that I also put?
Please, please.
So how anisotropic is the magnetic field response? Like if you rotate the magnetic field, how different are the responses?
So that is an excellent question. And I apologize, I should have said, but these are all measurements on powder samples. So we don't have that information. We would obviously need to grow crystals to study that. And I think particularly with these sort of ones with quite strong single ion anisotropy, that would be a way to really understand these things a little bit more.
Yes. Okay. Very nice talk. I'll follow up with an email to you. Thank you.
Okay.
Yeah. There is a second question by Manoranjan. Please, Manoranjan, are you there?
Yeah. Sean, nice talk. Thank you. I have a question regarding your 1/3 plateau. There are two compounds where you have the 1/3 plateau. Can you please tell me what is the origin of these plateaus?
So the answer is we don't really know.
Okay.
We observe them, and to really understand them a bit more, we would probably have to do, well, we would need to do neutron diffraction in an applied field to look at the magnetic structure. Because these are powders, it's quite difficult to do the in-field neutron studies, because so the projection of the field within, if you've got anisotropy, is going to be different depending on the orientation of the crystal.
Okay.
So I'm afraid I can't elaborate any more on that.
Okay, thank you.
Yeah. Thank you, Dr. Darton, for a nice talk, and thank you for attending this session here. So we will, fine. So we are going for the next one. The next speaker is Dr. Sanjay Singh from IIT BHU.
Yes.
Dr. Sanjay, are you
Yes.
there?
Yes, yes, I'm here.
Yeah. Okay, let it get on. I mean, I think, yeah. So you may please, yeah, it is shared. Yeah, fine. We can see your slides.
Yeah, thank you.
So great. So the topic of the talk is phase transitions and origin of structural modulation in magnetic shape memory Heusler alloys. So Dr. Sanjay, we are having 30 minutes time, 25 minutes for talk and 5 minutes for discussion. Please, you may start.
Thank you, Dr. Ghosh, and let me thank to the organizer for giving me this opportunity to present my work here.
So as you can see, the talk is based on the phase transition and the structural modulation. And here is the outline of my talk. So first I will introduce some of the basic terms which basically is responsible for the interesting properties of these alloys. Okay. So Martensite phase transition and shape memory effect and then modulation. Then I will present mainly result for this standard Ni2MNGA magnetic shape memory alloy, which is the only system which shows largest magnetic field induced strain till date, and then another system after the same system with small platinum doping. Okay. So let me start with the fundamental of martensitic transition. So if we see in the Middle Age, the knights generally heat their sword and then put in the quench water, and this gives them the hardness. Okay, this is basically very common in steel industry, and the origin behind this hardness is basically the martensite phase, and this process is known as martensite transition. So basically, if you have high temperature cubic austenite phase, so austenite is generally cubic, and then your system transforms to the martensite phase where you have twin structure. So it's microstructure, and so this is a general description, but if we see the crystallographic description of this martensite transformation, which was first given in iron carbon system. So basically, if you have a FCC lattice and due to lowering the temperature, you have crystallographic symmetry change. So basically, the symmetry is lowered, and generally it goes to the tetragonal phase, but it may be it can go to the orthorhombic or even lower symmetry phase, and this process is known as band distortion. So here we are talking about magnetic shape memory alloy. So in general, shape memory alloy are very common and very useful. So shape memory alloy have phase transition, this martensite phase transition, and if you go again to the austenite phase, they remember their shape. Okay? But suppose if you have a system which is magnetic in the martensite phase, so here, and these yellow and reds are different twin variants. So if it is magnetic, then different magnetic moments are aligned in different direction in different twin variants. Now you may have two conditions. Either in the first case, if you have low magnetic crystalline anisotropy, then in case if you apply field, the moments will try to align in the direction of the field, and there is no change in the shape in general. But on the other hand, if you have large magnetocrystalline anisotropy system, then together with this moment, the crystallographic or structural variants will also try to align in the direction of the field, and then you have shape change and large magnetic field induced strain, and which is maximum around 10% observed in this magnetic shape memory alloy, and the composition is Ni2MnG. And these magnetic shape memory alloy is also very much known as multiferroic shape memory alloy because they shows both ferromagnetic hysteresis and ferroelastic loop. But basically, the physical property wise, they are very much important, and due to different, the combination of different degrees of freedom with the magnetic degree of freedom, like magnetic plus electronic degrees of freedom gives, for example, here I showed the magnetoresistance behavior, interesting magnetoresistance. Then as I showed, told earlier that they give interesting magnetic shape memory effect, and due to this we have large magnetic field induced strain. And they also give magnetocaloric effect if the magnetic degree of freedom coupled with the thermal degree of freedom, and it has large practical importance. So as in the title, I have the origin of the modulation. So the first thing is that why modulation is important. Here modulation is basically used for structural modulation. So if you see the literature, it says that if a system is modulated, then you have low tuning stress. Low tuning stress means if you apply magnetic field, then your twin variants can easily move, and then you have large MFIs. So if you understand the modulation, the physics of the modulation, then we can design new alloys which have better functional properties, and we can also understand their existing physical properties. As I have mentioned that Ni2MnGA is the magnetic shape memory alloy. Till date, only this system can show 10% magnetic field induced strain, none of the other, although a lot of alloys were prepared in the past. Now, these this modulation is also important in magnetic in deciding magnetic property. For example, a recent report shows that how this Martensite phase and the modulation gives you the ischemionic phase. So not only to understand the magnetic shape memory effect, but to understand other physical or magnetic property, we need to understand the modulation. Because if structure is modulated and spin is coupled, then spin must be also modulated, and that can give different interesting properties. So let us first try to understand what are the modulated structure. So we all know from the crystallography that if we have a crystal, then if we take a unit cell, suppose here these are the unit vector A2 and A1. If you take a unit cell, this square, and then if you repeat in the space in any direction, then it's periodic and generate the crystal. But sometimes due to the external parameter, these atoms may disturb from their position, and they may get and we may have superstructure, which are called basically the modulated structure. So now here is the example in the right side. So suppose this atom, the first one shifted right and the second one is left, and then third one is again right. So if you try to define a unit cell, you can see that if we take this double unit cell, which is two times of this A2, then we can repeat this double unit cell and generate the whole crystal. So this is a type of two-fold superstructure, example of two-fold superstructure, and the system is known as commensurate modulation. Means even though you have modulated structure, but the periodicity is maintained. On the other hand, here the third case, here we have the atoms are shifted such that you will never able to find a unit cell which you can repeat and generate whole crystal with the multiply by integer number with the unit vector. For example, here you see you will never find any unit cell which you can repeat and generate the whole crystal. If you repeat this, then you see if you take the two times as in the earlier example, and if you see here, then you see this atom is shifted towards right. Okay, and the next is like, so you will never able to find either you take two times or three times. So these are the example of incommensurate modulated crystal, and these crystals come into the under the aperiodic crystal definition. Okay. So now in the reciprocal space, if you try to understand this, so suppose if we have a normal crystal, then you have well-defined Bragg reflections here, which are periodic. Now, if you have modulated structure, then you have extra reflection in between this very bright black. Here I have shown with the black spots. So you have extra spots, and these spots are known as satellite spots. So this black spot, which is equivalent to the crystal, there is no difference between in these spots. They are known as main reflection, and you have in between which are known as satellites. And depending on the distance between these satellites, it can be commensurate or incommensurate. If it is commensurate, then the distance between all spots will be equal. Yeah? So means the periodicity is maintained. Now, if you see the XRD pattern, then how we can observe this satellite reflection? So if you have a crystal and it's going to the modulated phase, then you see small peaks coming here together with the main satellite. So all these main reflections are present here, but together with that you have a small intensity peak. So this is the indication of modulated structure. Now, so in general, when we are doing the analysis of any diffraction pattern, we use a simple crystallography, which is called three-dimensional basically crystallography, and we use, so the reciprocal lattice vector is HA star plus KB star plus LC star. Okay, so only 3 and HKL are your Miller indices. But if you have incommensurate structure, and as I mentioned, that you have loss of periodicity. So that periodicity basically you can include if you take another dimension and include in this definition, which is known as this wave vector, modulation wave vector. And this M is another integer which tells you about the order of satellites. Like here. So this is your main reflection. So you can write HKL as usual. But the other one, this reflection, which is coming due to this modulation called satellite, you need another value of integer, which is m. So this is m equal to first means first order reflection, and m equal to 0 means the fundamental reflection. And q you can define like this. So if all values of this q1, q2, q3 are rational, then you have commensurate structure, and if at least one is irrational, then you have incommensurate structure. So this is just a definition. On the other hand, you can also try to find the atomic position using the modulation wave function. So coming to the our system, this nickel 2 manganese gallium magnetic shape memory Husserl alloy. So Husserl alloy I wrote because it has a Husserl structure. So Husserl formula x2yz, where the x sits. So this is FCC lattice with a space group FM3 bar m. So your x atom sits here in the equivalent position 8c, and then y and z are at the 0, 0, 0 and half position. Okay. So this system, why we study this system, because it shows the largest magnetic field induced state till date, and it has TC around 373K, so it shows magnetic transition, and then you have Martensite transition around 220K. But the important thing is here that the Martensite structure of this alloy is controversial from last 20 to 25 years, was controversial. So we try to understand this system, the structure of Martensite phase, and I told that the Martensite structure is basically responsible for all fascinating properties of these alloy. So if you see the literature, there are different reports. So if you see the nature of structural modulation, so what is the nature, whether it is commensurate and incommensurate. So there is a controversy, and in different literature, people report different things. And if you go to the physics or mechanism of structural modulation, that is also controversial. So some group report that it is the origin is charge density wave, means there is a modulation of commensurate or incommensurate, that is a separate issue. But basic is that there is a charge density wave and it is modulated. On the other hand, there is another theory which tells you, which report that the structure is not at all modulated. This is just a staking fault. So we try to understand the actual structure of this alloy. And so if you see the magnetization curve of Ni2MnGa, then you see there is a large increase in the magnetization, and this is correspond to Tc, and there is a large decrease here in the magnetization, which is correspond to the Martensite phase, because you have large anisotropy, so which drops the magnetization. But if you have another small kink in the magnetization, that is known as the precursor effect or pre-Martensite phase transition. And starting from shape memory alloy, standard shape memory alloy nitinol, which we all know it is well known in dental clinic and also for the angiography. So this also shows this phase, and till now it is known as the pre-Martensite phase or precursor effect, where cubic symmetry is preserved. So, so in this talk, I will basically presenting what is the nature of the modulation and what is the nature of this pre-Martensite phase, and we'll compare. So for that, we use the synchrotron X-ray diffraction data, because the synchrotron has higher intensity compared to the lab, and also it has very high resolution nowadays with the current generation of synchrotron. So we reported, we collected these three XRD pattern in three phases: austenite, which is cubic Husserl phase, and then pre-Martensite phase transition below, basically here, and then in the low temperature Martensite phase. If you zoom this, you can see in the cubic you have this large peak, and near to this you don't have anything. But when the system goes to the pre-Martensite phase, you have extra reflection, which are satellite reflection. And similarly in the Martensite, you have more number of satellite reflection. And also you see this peak is basically, instead of one peak, we have many peaks, which tells you that you have lower symmetry is lower compared to the cubic structure. Okay, so let us first try to understand the structure of Martensite phase. So the first thing what we did, we used the standard analysis procedure, which everybody is using nowadays, the three-dimension approach. So you take the whole X-ray diffraction pattern together and give the lattice parameters and try to refine this. But if if you see the refinement, so overall here looks better. Okay, but if you zoom in, you can see the observed peak, which are presented by this black circle, and the theoretically generated pattern is red, presented by red curve. They have a clear mismatch, which tells you that your lattice parameters are not correct. Okay? But the problem is, even if you change your lattice parameter or change the superstructure, or basically the degree of the modulation, 2 times or 3 times, but even you will not able to fit these reflections. Okay? So now next we move to the higher dimension approach and try to use the 3+1 dimension superspace group crystallography to understand this, where, as I mentioned, that we use one Q, which is modulation wave vector. So first we gave the rational number. Rational number means we tried with the commensurate model. This is equal to the 3-dimension model, and we try to fit it. And when we saw these reflections, and as you see here, this is 121, -1, and 2001. So here the m value is not equal to 0, means these are the satellite reflection. So the effect of modulation is always on the satellite, not on the main reflection. So if you see the satellite, the commensurate or rational values of Q is not able to properly fit this X-ray diffraction, the observed data, this black dot. Then we try to refine this Q, means in the program itself, you can refine that. And then you found that you can exactly match the position of the peak. So here I'm not telling about the shape of the peak, the position of the peak, which defines your lattice parameter. And you have very good agreement between experimental and theoretical pattern. And if you see the Q is, the value of Q is 3/7 plus delta, where the delta is degree of incommensuration. So this is irrational number, which tells you that the system is incommensurate. It is not a normal periodic structure. Now, in the next round, we try to look for more small intensity peak, and we found even if we take the first order satellite, there are some reflection, break reflection, which are still not indexed. And then we try to increase the order of the satellites, and then for m equal to 2, this result is presented here. And finally, all reflection we could analyze only if we take m equal to 3. And here is also one reflection. And the thing is, as we increase the order of m, the intensity of reflection is going down because this is higher order satellites. So all peaks were indexed with the third order satellite. And this is the final this pattern. If you can zoom it, and you can see even up to high angle data or low angle data, we have complete fitting. So this shows that you have m equal to 3. Now, using this knowledge, we can generate the reciprocal lattice pattern and try to understand what is the nature of the modulation. So here you can see, so these this is the 2-dimension pattern generated from the ritual refinement data. You can see these are the red dots, which are main reflection. Here I use m equal to 0. And we have green dot, and between 2 red dot, we have 6 green dot. So this is the order of satellite, but if you count, you have 6. And if you see closely, the distance between these dots is also different. So there are 6 dots, and distance is not even, means system has 7m modulated structure. So modulation is defined as n plus 1. So n is the order of reflection, or number of reflections. So we have 6. So 6 plus 1 is 7m type, and the distance is not same, means system is not periodic. And if you from this, you can also plot a 3-dimension structure. This is approximate, not the real, but you can see all the atoms. If you catch this gallium one, then it's going like a wave. So it has, we can say it has the modulated structure. Now, another interesting piece of information we got from this superspace group analysis is the evidence of Faison stain. So Faison stain is generally observed in quasicrystals where you have incommensurate or aperiodicity. So if you try to refine these satellite reflection, so here m is not equal to 0 means satellite only. All the information in this modulated structure are within the satellite reflection. So you see here, you try to refine this or fit these peaks, observed peaks, And if you use, we know that the broadening can be generated from strain or particle size. And the third is the temperature. The temperature model is given by the Stephen, so it is known as Stephen model. This is 3-dimension model. But if you take all these things, the normal 3-dimension strain and this broadening due to the thermal factor or Stephen model, then we could not fit this satellite reflection, and these reflection could be fitted only if we consider the 4-dimension strain tensor into the refinement, which tells you that you have this phase-on strain. And this was the first experimental report for phase-on strain using a simple this powder X-ray diffraction data.
Dr. Sanjay, we are having 5 minutes more.
5 minutes more. Okay.
Yeah, yeah.
Okay. So now just briefly mention about the pre-Martin side, because my next coming slides will be based on that. So you see, similarly for pre-Martin side, these are the satellite reflection, and with the similar way, this also we analyze and we find this is incommensurate. But here you just remember that the main reflections are still cubic-like. Okay. So now with this, I will go with the physics of the modulation. So we have only we have two models in the literature, as I mentioned earlier. One is adaptive model. So adaptive models tells you that you have this kind of structure. So due to staking fault, all atoms move. But you see here, all atoms moving in the same direction. Okay, either here or here with the same amount. On the other hand, with the charge density model, different atoms have different amplitude of modulation. Okay. So if we compare the positions, which gives you the amplitude of modulation, then you see we have position shifted in X direction as well as Y and Z direction. This tells you that the position shifting is not uniform. So the origin of modulation is basically charge density wave driven. Okay. This is the last few slides. I will show you one of the important results which we could obtain only because of super space group analysis. So as I mentioned that the precursor, this pre-Martensite phase was considered as a precursor effect where cubic symmetry is maintained and no band distortion, means no symmetry lowering. And even it started means everybody assumed starting from 1956, and still in 2015 paper you see they still report that it is a quasi-cubic kind of system. But when we and here is the example how, because you don't see any splitting in the P. But now when we took the platinum into Ni2MnGa, we could see the magnetization different here. See here the magnetization is going like this with a small kink here, but here you have two slopes. So we try to understand these two magnetization process, and we did the same analysis like we did for standard Ni2MnGa using the synchrotron XRD data, and we find that at 290K and 240K, so here, then above this and below this, we have simple structure as we observed for the Ni2MnGa. But something interesting goes on between here, between this slope and this slope. So if you try to understand the X-ray diffraction pattern around 225K, which is between the two slopes, then we find that if we start with cubic, it is not cubic. You can see there is a clear difference. Now, if you reduce the symmetry, you have better fitting, and the complete very good fit we obtain when we use the orthorhombic crystal structure. Okay, and this is the similar structure like the pre-Martensite phase people reported earlier, but the splitting of the P clearly tells that this structure is not cubic. So your symmetry is broken, and this was the important result, and which one can obtain using this super space group analysis. And we finally gave the phase diagram, this new phase diagram of this magnetic shape memory alloy, that you have two kinds of pre-Martensite phase. One is the cubic-like, other is band distortion. So basically, one should not consider the pre-Martensite phase as thermodynamically unstable phase. On the other hand, it is a thermodynamic stable phase. So finally, I will give the summary that we obtain the nature and origin of modulation in this Ni2MnGa shape memory alloy. And we can say that super space group cannot be only used to understand the crystal structure, but a lot of physics we can do using this higher dimension crystallography approach. And then finally, we discovered this, this new pre-Martensite phase, which was considered as precursor till date. Thank you.
Thank you, Dr. Sanjay Singh, for a very nice and detailed talk. So the floor is open for questions. So is there any question, please? Audience?
Hello, hi.
Yeah, please.
Okay, so I just wanted to know, what is the nature of the bones, whether is it covalent type or ionic type in this type of alloys? And what is the nature of the bonds in this type of alloys? And second is, if so, what are the oxidation number of nickel and manganese and gallium as well?
Okay, so the first question maybe I will ask you again because I could not understand. The second question is, this is the metallic system.
Okay.
The intermetallic system. So we don't talk about the oxidation state.
Okay.
And the first question I could not still. Can you just elaborate your question?
Okay, so so I was just asking, what is the nature of the type of the bonds? Is it covalent or is it ionic? Yeah.
These are metallic bonds, intermetallic bonds.
These are metallic bonds. Okay. And another question is, so the structure of the martensite phase is quite actually debatable. So some people say it's a kind of orthorhombic, and other people say it's tetragonal. So according to your experimental finding, what sort of structure is the martensite phase? Yeah.
Okay, so the structure of martensite depends on different alloy system, okay, or thermodynamic or temperature history. So it can be tetragonal also, it can be orthorhombic also, it can be monoclinic also. If you see the different system, they have different. But in this system, we have orthorhombic structure in the martensite.
Okay.
In this particular system.
Okay. And all those spin wave characteristic, we will be able to see only in the pre-martensite phase, the modulated structures that you mentioned.
So the modulated structure, we could see this pre-martensite one.
Okay, so all these spin features will be seen only in this particular phase only, right?
No, in both the phases, in the martensite phase also, and that is still a debatable question. Actually, if you have a modulated crystal structure, then one can think that spin must be modulated also. But that, because of this incommensurate nature of the crystallography, the theory is not able to predict even. And if you go to the neutron also, it's difficult to analyze, because now with the crystallography, it's fine that you can analyze. But I think one needs to look carefully about the magnetic structure. That's why I put that slide, that you have now this skyrmion thing. So you must have some non-polarity also, which is not reported from neutron still in this system.
Okay. So we can think
it's very interesting thing to investigate.
Okay, so we can think that particular this non-modulated, non-commensurate phase as a kind of spin liquid.
That I cannot comment on that. Spin liquid or spin liquid, but
Okay. Thanks a lot.
Okay, if there is no other questions, so thank you, the speaker, Dr. Sanjay, for this talk, and then we may conclude that session right now, the organizers. So
let's thank the Professor Nilutpal Ghosh for chairing the session. Thank you very much.
Thank you very much, Manoranjan.
So next session will start at 3 o'clock, and then we'll. So now we have a lunch break, and if someone is interested to discuss, it will be online. So people are free to discuss whatever they like. Thank you.